Hello there, and welcome to Life Beyond Seen, where the deep past surfaces slowly like light filtering down through water, and the strangest creatures in history become, for a little while, almost familiar. Tonight, we're going somewhere that no longer exists. A sea that once split an entire continent in two, warm and wide and teeming with life, pressing through the middle of what would one day become Kansas, Nebraska, South Dakota, the flat heartland of North America. A sea that vanished long before the first human being ever walked the earth. And somewhere in those warm, ancient waters, moving fast enough to catch almost anything it set its attention on, there was an animal most people have never heard of. Its name is Dolichorhynchops. It is a long name, and we all get comfortable with it as we go. But what matters right now, in this opening moment, is the image of it. A compact, powerful body cutting through warm, shallow water. 4 broad flippers working in long, sweeping strokes. A narrow snout lined with interlocking teeth, built for one purpose: speed, precision, the clean, efficient violence of a pursuit predator in its element. This is not a creature from a film. It did not make the cut for most popular dinosaur books. You will not find a plastic toy of it in the gift shop at the Natural History Museum, at least not easily. And yet Dolichorhynchops is one of the most completely documented short-necked plesiosaurs ever recovered from the fossil record. Multiple specimens, multiple species, bones preserved in remarkable detail in the chalk beds of the American Midwest. An animal we actually know quite a lot about, which makes it all the more interesting that it sits so quietly in the background of public awareness, while its more famous neighbours, the long-necked Elasmosaurus, the enormous Mosasaurs, the great winged pteranodons soaring above the same sea, tend to take up all the attention. Tonight, we are going to spend some time with this one, with Dolichorhynchops, with the world it lived in, the way it moved, what it hunted, what hunted it, what its bones have told us, and what its disappearance from the fossil record means in the context of a much larger story. Before we go any further though, I would love to know where you are right now. Where are you listening from tonight? Are you somewhere near water, a lake, a river, an ocean not so far away? Or are you deep inland, hours from anything that resembles a coastline? What does the water look like near you if there is any? Is it still and dark or moving, lit by something? The reason I ask is not just to say hello, though I do mean that warmly. It is because tonight's story is so much about a body of water, about what it felt like to be a living creature inside a particular sea, in a particular moment in deep time. And sometimes it helps to start with the water, before we travel to the water that no longer exists. If you enjoy this kind of quiet, careful exploration, I would genuinely appreciate it if you took a moment to like this video and subscribe to Life Beyond Seen. It is a small thing that makes a real difference in helping this channel find other people who might enjoy spending a late evening with a vanished world. Thank you. Now let us go back. A long way back. Roughly 85 million years ago, the continent of North America did not look anything like it does today. The Rocky Mountains were still in the early stages of forming. The Great Plains were not plains at all, and running directly through the middle of the continent from what is now the Arctic Ocean in the north, all the way down to the Gulf of Mexico in the south, was an inland sea. A shallow, warm, brackish body of water that geologists and paleontologists call the Western Interior Seaway. It was not a narrow channel. At its widest, it stretched somewhere around 1,000 miles across. It was not a deep abyss either, not by ocean standards, reaching perhaps 600 to 900 feet at its greatest depth. But it was enormous in terms of what it contained and what it meant for the life of the continent. It effectively split North America into 2 separate land masses. A western land mass called Laramidia, where the ancestral Rocky Mountains were beginning to push upward, and an eastern landmass called Appalachia, lower and warmer, draped in dense subtropical vegetation. Between them, the seaway moved. Warm, restless, full of things that wanted to eat, and things that were trying not to be eaten. The surface of that sea, if you could have hovered above it 85 million years ago, might have looked deceptively calm. Light catching the small chop of waves, the distant smudge of land on both horizons, the occasional dark shape breaking the surface, something large, something breathing, then gone. But beneath that surface, the water was anything but quiet. The seaway was ecologically dense in a way that is almost difficult to picture. Fish in enormous numbers, ammonites spiralling through the water column, soft-bodied cephalopods moving in pulses of jet propulsion, diving birds called hesperornithiforms paddling down from the surface, and moving through all of it, the large predators. Mosasaurs, sharks, plesiosaurs, animals that had evolved over millions of years to be very good at killing things in warm, shallow water. This is the world Dolichorhynchops was part of, not a peripheral player in it, a central one, a predator shaped by the specific pressures of this specific environment, built to move quickly through warm, shallow water, to chase fast prey, to survive in a sea where the competition was fierce and the stakes were always high. The name Dolichorhynchops comes from Greek roots. It roughly translates to something like long-snouted face, which is, once you see a reconstruction of the skull, a fairly accurate description. The snout is long and narrow, tapering forward, and the jaws are lined with conical interlocking teeth, the kind of teeth that are very good at gripping slippery fish, and not particularly useful for crushing bone or tearing thick hide. The name was formally established in 1902 by a paleontologist named Samuel Wendell Williston, working from specimens recovered in the chalk deposits of Kansas and Nebraska. We will come back to Williston and the story of how this animal was found, because that story is worth telling in its own right. For now, what matters is the shape of the animal. Compact, built low and wide, 4 large paddle-like flippers extending from a streamlined torso. The neck was short, noticeably short, which set Dolichorhynchops apart from the long-necked plesiosaurs that tend to define the popular image of the group. When most people picture a plesiosaur, they think of something with an improbably long neck reaching up from the water, like a snake attached to a turtle. That image has its own problems, which we will get to later in the story. But Dolichorhynchops was not that animal at all. The neck was compact and functional, reducing drag in the water, contributing to a body plan that was clearly oriented around speed and maneuverability, rather than the slow, patient ambush style that some of its longer-necked relatives may have employed. Total body length ran somewhere between roughly 3 and 5 meters, depending on the species and the individual specimen. Not enormous by the standards of the western interior seaway, where some of the mosasaurs were pushing 12 meters or more, but not small either. 3 to 5 meters of fast-moving predator in relatively shallow water is a significant presence. There are 2 main recognised species. Dolichorhynchops osborni, the first described, and Dolichorhynchops herschelensis, identified from material found in Saskatchewan. They were similar in overall form, with some differences in proportions and geographic range, and we will look at those distinctions more carefully when we examine the classification debates that have surrounded this animal and its relatives. What is interesting, even at this early stage of the description, is how the body of Dolichorhynchops reads as a kind of solution, an answer to a specific set of environmental questions. How do you catch fast prey in open water? How do you avoid being caught yourself? How do you compete in an ecosystem where almost everything else is also fast, also well-equipped, also shaped by millions of years of evolutionary pressure? The answer that Dolichorhynchops arrived at was a particular combination of speed, precision, and agility. A short neck to reduce drag, a streamlined torso, 4 large flippers generating powerful thrust, a long, narrow jaw for snatching rather than crushing. Every feature of the body points in the same direction, toward pursuit, toward speed. But the full meaning of that body plan only becomes clear when you understand the world it was operating in. And that world, the western interior seaway in the Campanian stage of the Late Cretaceous, was one of the most ecologically rich and dangerous marine environments that has ever existed on this planet. Every animal in it was either very good at hunting or very good at not being hunted, usually to some degree both. Dolichorhynchops had to be both things simultaneously, and the evidence suggests it managed that balance rather well for several million years. The fossil record that preserves this animal is itself remarkable. The Niobrara Chalk Formation, a thick sequence of fine-grained limestone and chalk deposited on the floor of the seaway, runs across parts of Kansas, Nebraska, and into surrounding states. It is one of the most productive marine fossil sites in the world. The fine sediment preserved bones in exceptional detail, sometimes articulated, sometimes with soft tissue impressions, sometimes with stomach content still identifiable after 80 million years. The Niobrara has given us not just Dolichorhynchops, but Elasmosaurus, Tylosaurus, Pteranodon, the enormous predatory fish Zephactinus, and dozens of other species that together paint an extraordinarily detailed picture of a vanished sea. It is because of that formation, and the generations of paleontologists who have worked within it, that we know as much as we do about Dolichorhynchops. It is not a mystery animal. It is not a creature reconstructed from a single fragment of bone. It is, in the language of paleontology, reasonably well known, and that is what makes it such a useful lens for understanding the Western Interior Seaway as a whole. So before we look at the animal itself in closer detail, its anatomy, its locomotion, its hunting behaviour, the remarkable fossils that have revealed how it reproduced and what it feared, it helps to spend a little more time in the world it inhabited. Because Dolichorhynchops did not exist in a vacuum. It existed in a specific place, at a specific moment in the history of this planet, surrounded by specific animals, shaped by specific pressures. The seaway that formed its world, its hunting ground, its danger, and ultimately the context for its extinction, is the right place to begin. The Western Interior Seaway is not easy to picture if you're standing in the middle of Kansas today. You would be looking at flat farmland, grain elevators, dry summer heat, and a sky that goes on longer than seems reasonable. There is no water in sight, or at least not the kind of water we're talking about. But roughly 85 million years ago, you would have been standing at the bottom of a warm, shallow sea. The land beneath your feet would not have existed. There would have been only water above you, perhaps 200 meters of it, sunlit near the surface and dimming slowly toward the soft sediment of the floor. A sea that stretched from what is now the Arctic Ocean all the way down to the Gulf of Mexico, cutting the North American continent cleanly in two for millions of years. The scale of this is worth sitting with for a moment. The seaway was not a lake. It was not a bay or an inlet. At its widest, it spanned roughly 1,600 kilometers from east to west, which is something close to the distance between London and Moscow. From north to south, it ran the full length of the continent, somewhere around 4,000 kilometers at its greatest extent. Depth varied considerably depending on location and time period, but in its deeper central zones, estimates suggest somewhere between 180 and 270 meters, with some portions possibly deeper. It was not an ocean in the deepest sense, but it was vast and it was warm. Surface temperatures in the Campanian stage of the Late Cretaceous, roughly 85 to 80 million years ago, were significantly higher than modern ocean temperatures at equivalent latitudes. The world was in a greenhouse phase. There were no polar ice caps. Sea levels were dramatically higher than today, which is precisely why an inland sea of this size was possible at all. The water itself was brackish in places, particularly near river deltas where fresh water drained from the surrounding land masses. It was not perfectly saline ocean water throughout, and that variation in salinity and chemistry likely influenced which animals could live in which zones. The chemistry of the seaway was not uniform, and neither was its depth or its productivity. Some areas were richer in nutrients, more productive, more densely populated with life. Others were quieter, more sparsely inhabited. The seaway was not a single homogeneous habitat. It was a mosaic of conditions, and the animals that lived within it were distributed across that mosaic, according to their own preferences and tolerances. To the west of the seaway lay the landmass that paleontologists call Laramidia. This was the western portion of what would eventually become North America, a long narrow strip of land running roughly along the line of the modern Rocky Mountains and extending westward. Laramidia was geologically active, with volcanic highlands, river systems draining eastward into the seaway, and a warm, humid climate that supported dense vegetation and an extraordinary diversity of dinosaurs. Triceratops, Pachycephalosaurus, Ankylosaurus, and dozens of other species would eventually evolve here, though in the Campanian stage the dinosaur fauna of Laramidia was somewhat different. Hadrosaurs were abundant, ceratopsians were diversifying, tyrannosaurs were present, though not yet the giants they would become later. The rivers that flowed from Laramidia into the seaway carried sediment, nutrients, and organic material that helped sustain the marine ecosystem. To the east lay Appalachia, the eastern landmass, which occupied roughly the area of the modern eastern United States. Appalachia was lower lying and more heavily forested in many areas. Its rivers also drained westward into the seaway. Between these two land masses, the seaway functioned as a kind of biological corridor and barrier simultaneously. Animals on Laramidia could not easily reach Appalachia, and the reverse was also true. The seaway kept the terrestrial faunas of east and west separate, which drove divergent evolution on both sides. But in the water itself, the corridor ran the full length of the continent, connecting Arctic waters to tropical ones, allowing marine animals to move freely across an enormous latitudinal range. The life within the seaway was extraordinary in its diversity and density. The fossil record from the Niobrara chalk and related formations gives us a picture that is unusually detailed for a marine environment this old. At the base of the food web were microscopic organisms, the plankton and phytoplankton that bloomed in the warm, nutrient-rich water. These supported vast populations of invertebrates, including ammonites, which were coiled cephalopods related to modern nautiluses, ranging in size from a few centimetres to over a metre in diameter. Ammonites were enormously abundant in the seaway, and their shells are among the most commonly recovered fossils from Niobrara deposits. They were prey for many animals, and their shells sometimes preserve bite marks that allow us to identify their predators. Fish were present in staggering variety. Encodus was one of the most common species, a medium-sized predatory fish with prominent fang-like teeth at the front of its jaws, fast and agile, a significant prey item for larger predators. Similichthes was another fast-moving predatory fish, longer and more robust. Bananogmius was a large, deep-bodied fish, somewhat like a modern tarpon in general form that could reach lengths of over a metre. And then there was Xiphactinus, the largest bony fish in the seaway, which could exceed 6 metres in length and was itself an apex predator of fish. A famous Xiphactinus specimen recovered from the Niobrara was found with a nearly intact Gillicus fish inside its stomach, suggesting it had swallowed its prey whole shortly before dying. The seaway was full of moments like that. Predators eating, predators being eaten, the whole system running at a pace and intensity that is difficult to fully appreciate from the quiet distance of the present. Sharks were present throughout the seaway, and among them Squalicorax is particularly notable. Squalicorax was a medium-sized shark reaching perhaps 3 metres, with distinctive serrated teeth well suited to cutting flesh and bone. It appears to have been something of a scavenger as well as a predator, and its teeth have been found embedded in the bones of many different animals, including plesiosaurs and mosasaurs, which suggests it fed on carcasses as well as live prey. Cretoxyrene, sometimes called the Ginsu shark, was larger, more powerful, and has been implicated in attacks on mosasaurs and other large marine reptiles. The sharks of the seaway were not background characters. They were active participants in the ecology, and their presence would have been felt by every other animal in the water. The mosasaurs deserve particular attention, because they were the dominant large predators of the seaway during its later stages. and they would have been an ever-present reality in the life of Dolichorhynchops. Mosasaurs were marine lizards, relatives of modern monitor lizards, that had adapted so completely to aquatic life that they could no longer come ashore. They ranged enormously in size and form. Platecarpus was a mid-sized mosasaur, relatively slender, probably a pursuit predator of fish. Tylosaurus proroger was something else entirely. It reached lengths of 12 to 13 meters, making it one of the largest predators in the seaway, and its skull was massive, armed with large, conical teeth suited to seizing large prey. Tylosaurus has been found with stomach contents including fish, sharks, diving birds, and other marine reptiles. It was not a specialist, it was a generalist apex predator, and Dolichorhynchops, at 3 to 5 meters, would have been an entirely plausible meal. The diving birds of the seaway are often overlooked in popular accounts, but they were a significant part of the ecosystem. Hesperornithiforms were a group of large, flightless diving birds, some reaching over 1.5 meters in length, that were highly adapted for underwater pursuit of fish. They had reduced wings, powerful legs positioned far back on the body for propulsion underwater, and toothed jaws, which is not something you see in modern birds. Hesperornis itself is the best-known genus, and multiple specimens have been recovered from Niobrara deposits. These birds occupied a niche somewhat similar to modern penguins or loons, hunting fish in the upper water column. They would also have been prey for larger predators. The seaway was not kind to anything that was not paying attention. What this ecological portrait describes is not a peaceful sea. It was a system under constant pressure, constantly churning, constantly adjusting. Every animal in it had been shaped by the same basic forces: find food, avoid being food, reproduce, repeat. The competition was not just between predator and prey, it was between predators competing for the same prey, between prey species competing for the same resources, between animals of similar size and strategy, jostling for position, in an ecosystem that had limited room at the top and enormous pressure from below. The Niobrara fossil beds, where so many of these animals have been recovered, sometimes in remarkable density, suggest that the seaway was genuinely productive, genuinely full of life in a way that is hard to parallel in modern marine environments of comparable depth and size. The time frame matters here as well. The Campanian stage of the Late Cretaceous runs from approximately 83.6 to 72.1 million years ago. Dolichorhynchops appears in the fossil record toward the earlier part of this window, roughly 85 to 80 million years ago, though the precise range depends on which specimens and which dating methods you're working from. This was not the very end of the Cretaceous. The famous mass extinction that ended the dinosaurs and the last of the large marine reptiles was still roughly 15 to 20 million years in the future from the peak of Dolichorhynchops. The seaway was at or near its maximum extent during this period. It was deep enough, warm enough, and productive enough to support the extraordinary diversity of life that the Niobrara preserves. It is worth noting that the seaway's existence was not permanent. It had formed during the earlier Cretaceous as sea levels rose and the continent subsided in its central regions, and it would eventually drain away as the Rocky Mountains began their uplift and sea levels fell. But during the Campanian, none of that ending was visible yet. The water was warm, the ecosystem was thriving, and the animals within it had no reason to suspect that the world they were adapted to would not last. Dolichorhynchops had been shaped by this world over millions of years of evolution. Its body, its teeth, its speed, its behaviour, all of it was a response to the specific pressures of this specific place at this specific time. Understanding the context does not just add colour to the story of Dolichorhynchops. It is genuinely necessary for understanding why the animal was built the way it was. The short neck, the large flippers, the narrow jaws, the compact torso, none of these features make full sense in isolation. They make sense as solutions to the problems posed by the western interior seaway in the late Cretaceous Campanian. How do you catch fast, agile fish in warm, clear water when you're sharing that water with mosasaurs that can swallow you whole, and sharks that will take a bite out of you whether you are alive or not. You evolve a body that is fast enough to pursue prey and maneuverable enough to avoid becoming prey yourself. You evolve a jaw that can snatch rather than wrestle. You evolve a form that reduces drag and maximizes thrust. That body plan, and the specific features that define it, is where the story of Dolichorhynchops really begins to get interesting. So let us look at that body plan directly. Let us slow down and actually examine what Dolichorhynchops was, from the shape of its skull to the structure of its flippers, because the details matter here in a way that goes beyond simple description. This was not a generic marine reptile. It was a highly specific animal, refined by evolution, into something that solved a very particular set of problems. The total length of Dolichorhynchops varied depending on the species and the individual specimen, but the general range sits between roughly 3 and 5 meters. That puts it somewhere in the size territory of a large modern dolphin or a small great white shark. Not enormous by the standards of the seaway, but not small either. It was a substantial animal. Something you would notice immediately if you were in the water with it, and something that would have registered as a genuine threat to the fish and squid it was hunting. The body itself was compact. Not in the sense of being stubby or awkward, but in the sense of being tightly organised, with relatively little wasted volume. The torso was broad and somewhat flattened, giving the animal a low-drag cross-section when moving through the water. There was no long, flexible tail in the way that fish or mosasaurs had. The tail of Dolichorhynchops was short, probably not a major source of propulsion, which tells us something important about how it moved. The power came from elsewhere. 4 large, paddle-shaped flippers dominated the body plan. These were not small steering fins. They were the primary engines of locomotion, long and broad, built for generating thrust rather than just redirecting it. The front pair was generally larger than the rear pair, though both were substantial. The internal bone structure of these flippers was highly modified from the ancestral limb bones of land-dwelling reptiles. You can still trace the humerus, radius, ulna, and the finger bones packed densely together inside the paddle, but they had been reshaped by millions of years of selection into something that worked far better in water than on land. Dolichorhynchops could not have walked on these. It was entirely committed to the sea. The neck was short. This is one of the most immediately recognisable features of the polycotylid body plan, and it is also one of the most functionally significant. If you have seen images of Elasmosaurus, the long-necked plesiosaur with a neck that accounts for more than half its total body length, Dolichorhynchops looks almost like a different kind of animal by comparison. The neck of Dolichorhynchops was not drastically longer than the head itself. It connected the skull to the torso without a great deal of ceremony, which from a hydrodynamic standpoint was a significant advantage. Less neck means less drag, less oscillation, less surface area for the water to push back against. The short neck was not a primitive feature or a simplification. It was an adaptation, a deliberate reduction in the service of speed. The skull was large relative to the body, and the snout was long and narrow. This is actually where the name comes from. Dolichorhynchops is built from Greek roots. Dolichos, meaning long, rhynchos, meaning snout or beak, and ops, meaning face or eye. Long-snouted face is a reasonable translation, and it is accurate. The snout projected forward in a way that would have been immediately obvious in life, giving the animal a somewhat elongated, almost gharial-like profile when viewed from above. The jaws were lined with conical teeth, interlocking when the mouth closed, which is a design you see in animals that need to trap slippery, fast-moving prey. These teeth were not built for crushing shell or grinding bone. They were built for puncturing and holding, for closing around a fish and not letting go. The whole jaw apparatus was built around the single task of catching things that did not want to be caught. Eye placement in Dolichorhynchops is worth noting. The orbits, the bony sockets that house the eyes, were positioned in a way that suggests at least some degree of binocular overlap in the visual field. This is not trivial. Binocular vision, where the fields of both eyes overlap in front of the animal, is associated with depth perception, and depth perception is extremely useful if you're trying to judge the distance to a moving target. Modern pursuit predators tend to have more forward-facing eyes than ambush predators, which often have eyes positioned more to the sides for wide-field surveillance. The eye placement in Dolichorhynchops fits the pursuit predator model, at least to a degree that researchers have found worth remarking on. There were two main recognised species. Dolichorhynchops osborni is the better known of the two, the one described first, and the one represented by the most complete specimens. The species name honours Henry Fairfield Osborn, the American paleontologist who was a prominent figure in early 20th century natural history, associated with the American Museum of Natural History in New York. Dolichorhynchops herschelensis is the second species, known from material found in Saskatchewan, Canada, and it was somewhat larger than Osborni, with proportional differences in the skull and limbs that suggest slight ecological or behavioural differences, though the broad outlines of the body plan were consistent between them. Both species were inhabitants of the Western Interior Seaway, and both fit the same general description of a compact, fast fish-hunting polycotylid. Weight estimates for animals like this are inherently uncertain. Paleontologists use the dimensions of bones to reconstruct body volume, and from body volume they estimate mass, but the calculations depend on assumptions about tissue density, fat distribution, and overall body shape that cannot be directly verified from fossils. For Dolichorhynchops osborni, estimates in the scientific literature tend to fall somewhere in the range of roughly 100 to 200 kilograms, possibly more for larger individuals, though the specific numbers vary depending on the methods used. For comparison, a large male bottlenose dolphin weighs around 200 to 300 kilograms, so the general scale is similar, though the body plans are of course quite different. The skin of Dolichorhynchops is genuinely unknown. No skin impressions have been found for this animal, which is not unusual. Skin is soft tissue, and soft tissue preservation in marine reptiles is rare. What we do have for comparison are skin impressions from ichthyosaurs, which are an unrelated group of marine reptiles that lived earlier in the Mesozoic, and from a small number of other marine animals from the period. Ichthyosaur skin impressions suggest a smooth, relatively scale-free surface, more like a dolphin or a shark than like a lizard. Whether plesiosaurs had similar skin is genuinely speculative, but the comparison is reasonable. An animal that spends its entire life in the water and relies on speed and maneuverability is not well served by rough, drag-inducing skin, so a smooth or near-smooth exterior makes functional sense. Some researchers apply counter-shading as a working assumption for the colour pattern, darker on top and lighter on the underside, which is a common camouflage strategy in modern marine predators. It helps break up the silhouette when viewed from above against the deeper dark water and from below against the brighter surface. But this is genuinely speculative, and anyone who tells you they know what colour Dolichorhynchops was is working from analogy, not direct evidence. The internal skeleton, of course, is what we actually know, and the skeleton of Dolichorhynchops is well documented across multiple specimens, which is one of the reasons this animal is scientifically valuable. The vertebral column was relatively short and stiff compared to many other reptiles, consistent with a body plan that relied on flipper propulsion rather than body undulation. The ribs were robust, contributing to a barrel-shaped torso that would have provided structural support for the large muscles needed to drive the flippers. The pectoral and pelvic girdles, the internal bony structures to which the flippers attached, were large and well developed, reflecting the enormous muscular demands of four-flipper propulsion. You can see the logic of the whole system when you look at it together. A compact stiff torso, large girdles for flipper attachment, broad flippers for thrust, a streamlined neck, and a long snout for catching prey. Every part of the skeleton is oriented toward the same functional goal. What is interesting is how different this body plan is from the other large plesiosaurs of the same ecosystem. Elasmosaurus, which is the animal most people picture when they think of plesiosaurs, had a neck containing more than 70 vertebrae and accounting for roughly 14 meters of its total 18-meter length. The head was small, the body was large, and the whole system seems to have been optimized for a completely different hunting strategy, possibly slow stalking with the long neck used to approach prey from below or from a distance before striking. Dolichorhynchops had none of that. Its neck was short, its head was large, and its whole body was oriented toward active pursuit. These two animals lived in the same sea, sometimes in overlapping time ranges, and they were solving the problem of being a large marine predator in completely different ways. The two species of Dolichorhynchops are not the only polycotylids in the Niobrara. Trinacra miramboneri is another, and it shared the seaway during overlapping time periods, with a similar but not identical body plan. How these animals partitioned the available resources, whether they competed directly or occupied slightly different niches, is a question that fossil evidence alone cannot fully answer. But the existence of multiple polycotylid species in the same depositional environment does suggest that the seaway could support more than one version of this basic body plan, which in turn suggests there was enough prey diversity and abundance to go around. Looking at the skeleton of Dolichorhynchops as a whole, what you see is an animal that was very specifically built. Not a generalist, not a flexible opportunist in the way that some large predators are, but something refined and committed. Every structural feature points toward the same behavioural profile: fast, active, pursuit-oriented, fish-focused, and highly adapted to the specific conditions of a warm, productive inland sea. The body is a record of the pressures that shaped it, and those pressures were real and constant. Which brings up the obvious next question. The body plan points towards speed. The compact neck, the broad flippers, the streamlined torso, all of it suggests an animal built for rapid movement through the water. But how fast could Dolichorhynchops actually go? And how do scientists even begin to estimate the swimming speed of an animal that has been dead for 80 million years? That question is more answerable than it might seem, and the methods used to approach it reveal something genuinely interesting about how paleontologists think about locomotion in extinct animals. The question of how fast a prehistoric animal moved is one that comes up often in paleontology, and it is usually answered with a great deal of careful hedging. For land animals, there are trackways, the preserved footprints left in ancient mud that can tell researchers something about stride length, gait, and pace. For swimming animals, the evidence is less direct. There are no trackways in water. What remains are bones, and from bones, researchers have to reconstruct the entire mechanical system of movement, estimate the forces involved, and work backward to something resembling a speed range. It is a legitimate scientific process, but it requires assumptions at every step, and those assumptions matter. The foundational framework for understanding plesiosaur locomotion is what researchers call the underwater flight model. The term sounds slightly dramatic, but it is a precise description of what the mechanics actually resemble. When an animal moves through water using large wing-shaped flippers in a rhythmic stroke, the movement is functionally similar to the way a bird moves through air. The flipper generates lift, and that lift produces forward thrust. The animal is not paddling in the simple back and forth sense that the word paddle might suggest. It is flying just through a denser medium. Penguins do this. Sea turtles do this. Dolphins use a different system based on vertical tail movement, but the principle of generating thrust through appendage motion is the same. Plesiosaurs, based on the structure of their limbs and girdles, appear to have been underwater flyers, and the four-flipper arrangement is what makes them particularly interesting. Most animals that swim using appendages use either two limbs or rely primarily on the tail. Plesiosaurs used all four flippers simultaneously, which raises a question that researchers have worked to answer for decades. How did those four flippers interact? Did they all stroke together? Did they alternate? Did the front pair and the back pair operate on different timing cycles to avoid interfering with each other? In 2004, researchers S. Chatterjee and R.J. Templin published a detailed hydrodynamic analysis of plesiosaur locomotion that attempted to model the mechanics of this system. Their work drew on fluid dynamics, comparisons with modern animals, and the physical dimensions of plesiosaur skeletons to build a picture of how the locomotion actually worked. One of their findings was that the four-flipper system was likely not simply redundant, meaning the animal was not just using twice as many flippers to go twice as fast in a simple linear way. The interaction between the front and rear flippers, the way water disturbed by one set of flippers affected the performance of the other, was a real mechanical consideration. Their analysis suggested that when properly coordinated, the four-flipper system could be genuinely efficient, producing strong thrust with relatively low drag. For the short-necked polycotylids like Dolichorhynchops specifically, the body plan offered some advantages that longer-necked forms did not have. The neck in Elasmosaurus, to use the extreme example, was not just long, it was a drag-producing structure. Moving through water, a long neck creates resistance. It interrupts the streamlined flow of water around the body. It has to be held in some position, and any position that deviates from perfectly aligned with the direction of travel adds drag. Dolichorhynchops had almost none of that problem. The short neck meant the transition from head to torso was compact and smooth. The skull flowed into the body with relatively little interruption. From a pure hydrodynamic standpoint, the polycotylid body plan was more streamlined than the elasmosaurid one, and more streamlined bodies move faster for the same amount of muscular effort. The flipper surface area relative to body size also matters here. Larger flippers relative to body mass can generate more thrust, and polycotylids had flippers that were proportionally quite substantial. The pectoral and pelvic girdles in Dolichorhynchops were large and robust, indicating the attachment points for correspondingly large muscles. Those muscles were the engine. The flippers were the propellers. A compact torso, large girdles, broad flippers, and a streamlined profile. When you put those features together, you get an animal that the physics of fluid dynamics would predict to be a capable and potentially fast swimmer. Actual speed estimates, though, are where things become appropriately uncertain. Based on hydrodynamic modelling and comparisons with modern analogues, some researchers have estimated that polycotylids like Dolichorhynchops could achieve burst swimming speeds in the range of roughly 3 to 4 meters per second. To give that a sense of scale, 3 meters per second is approximately 10 to 11 kilometers per hour, which in water is genuinely fast. For comparison, an Olympic swimmer at full sprint reaches around 2 meters per second. A leatherback sea turtle, which is one of the better modern analogues for large flippered marine animals, can reach burst speeds of around 2 to 3 meters per second. Dolphins, which are built for speed in a different way, can sustain around 5 to 7 meters per second and burst considerably higher, but dolphins have a fundamentally different locomotion system and are not direct comparisons. The point is that the estimates for Dolichorhynchops place it in a range that is meaningfully fast for a large marine animal, fast enough to be a serious pursuit predator. It is worth being clear about what these estimates actually represent. They are not measurements. No one has watched Dolichorhynchops swim. The numbers come from computational models that take the dimensions of the skeleton, make assumptions about muscle mass and flipper shape, apply known principles of fluid dynamics, and produce a range of plausible values. Different models, different assumptions, different ranges. Some estimates are more conservative, some push toward the higher end. The honest answer is that we know Dolichorhynchops was built for speed. We have reasonable physical grounds for estimating a speed range, and we have modern analogues that make those estimates plausible, but we cannot be certain of the exact numbers. That uncertainty is not a failure of science. It is just the reality of working with incomplete evidence from very deep time. What the modern analogues do offer is a way of thinking about what speed meant for an animal like this in behavioural terms. Consider the Humboldt squid, which is one of the faster and more agile cephalopods in modern oceans, capable of rapid directional changes and bursts of speed when pursuing prey or evading predators. Or consider a bluefin tuna, which is built around the same basic principle as Dolichorhynchops in a different body plan. streamlined, powerful, fast, and oriented toward active pursuit of mobile prey. These animals do not sit and wait. They chase. Their speed is not just a defensive capability. It is the core of their hunting strategy. The body of Dolichorhynchops, with its compact form and large flippers, suggests the same orientation. This was an animal that moved toward its prey rather than waiting for prey to come to it. There is also the question of maneuverability, which is related to but distinct from raw speed. A very fast animal that cannot turn quickly is less effective as a predator than a moderately fast animal that can change direction rapidly. The four-flipper system of plesiosaurs may have offered some advantages in maneuverability as well as speed. By varying the stroke of individual flippers, an animal could potentially generate turning forces in multiple directions. The short neck of Dolichorhynchops also meant that the head could be reoriented more quickly than in a long-necked form, which matters when you're trying to track and intercept a fish that is changing direction every fraction of a second. Exactly how maneuverable Dolichorhynchops was is difficult to quantify, but the structural features are consistent with an animal that could handle the rapid directional demands of active fish pursuit. One comparison that is often made in discussions of plesiosaur locomotion is to penguins, and it is a useful one. Penguins are not large animals, but they are extraordinarily effective underwater swimmers, using their wing-shaped flippers to generate thrust in a way that is mechanically similar to the plesiosaur model. A Gen 2 penguin can reach speeds of around 8 to 9 km per hour underwater during pursuit dives. They are agile, fast relative to their size, and capable of catching prey that is itself trying to escape. The penguin comparison is obviously imperfect, because the scale is completely different and the body plans diverge in many ways, but the basic locomotion mechanism is similar enough to be informative. If a small animal using underwater flight can achieve those speeds and that level of agility, a much larger animal with proportionally larger flippers and more muscle mass behind them has the potential for impressive performance. The limits of speed estimates from fossil data are real, and it is worth sitting with them for a moment. The skeleton tells us about the hardware. It tells us the dimensions of the flippers, the robustness of the girdles, the shape of the torso, the length of the neck. What it cannot tell us directly is how much muscle was there, how efficiently that muscle operated, how the nervous system coordinated the four flippers, or how the animal actually behaved in the water on a moment-to-moment basis. These are gaps that modelling can partially bridge, but not close entirely. The speed estimates for Dolichorhynchops are informed estimates, not measurements, and they carry the uncertainty that comes with that distinction. What the body plan does tell us with more confidence is the general category of predator this animal was: the compact, streamlined form, the large flippers, the short neck, the long, tooth-filled snout. These features together point toward an active pursuit predator rather than an ambush predator or a slow, patient stalker. An ambush predator is typically camouflaged, sedentary, and built to strike quickly from a stationary position. A slow stalker, like the long-necked elasmosaurids, may have relied on patience and the reach of that extraordinary neck to approach prey without triggering an escape response. Dolichorhynchops does not fit either of those profiles. It fits the profile of an animal that found its prey and then went after it, using speed and agility to close the distance before the prey could escape. That is a specific and demanding ecological role. It requires not just physical capability, but the behavioural and neurological machinery to support it. The ability to track moving targets, to anticipate direction changes, to coordinate rapid limb movements, and to sustain effort over the duration of a chase. None of that is directly preserved in the fossil record, but all of it is implied by the body plan. The skeleton is the record of what the animal needed to do, and what it needed to do was move fast and catch things that did not want to be caught. Speed, then, is not just a physical attribute in the story of Dolichorhynchops. It is the organising principle of the animal's entire way of life. The body was built around it. The hunting strategy depended on it. The ecological role required it. Understanding how this animal moved is not a separate question from understanding how it lived. They are the same question asked from different angles, and the answer, incomplete as it necessarily is, points consistently in one direction. This was an animal that earned its place in the seaway through velocity, through the ability to move through warm, productive water faster than the fish it was chasing. But speed alone, as useful as it is, only takes a predator so far. The other half of the equation is what happens when it gets there, what the animal actually did with those teeth, and how the hunting itself worked in practice. So we arrive at the teeth, and the teeth are where the hunting story actually begins. The jaws of Dolichorhynchops were long and narrow, tapering toward the tip in a way that would have reduced water resistance during a strike. The teeth themselves were conical, slightly curved, and interlocking when the mouth closed, meaning that when the jaws snapped shut around a fish, the teeth meshed together rather than simply pressing against each other. This is a very specific design. It is not built for crushing shells, grinding plant material, or tearing chunks of flesh from a large carcass. It is built for one thing: seizing and retaining a small, slippery, fast-moving animal that is trying very hard to escape. Once those interlocking teeth closed around a fish, getting out would have been nearly impossible. The fish would have been gripped from multiple directions simultaneously, and the curved shape of the teeth would have worked against any attempt to slide free. It is a trap, essentially, built into the anatomy of the skull. This matters because it tells us something specific about the prey Dolichorhynchops was targeting. Animals with crushing dentition, like some Mosasaurs, were going after hard-shelled prey. Ammonites, turtles, shellfish. Animals with blade-like serrated teeth were cutting through larger, meatier prey. The simple conical, interlocking teeth of Dolichorhynchops point clearly toward fish and soft-bodied cephalopods, animals that need to be grabbed quickly and swallowed whole or in large pieces, not chewed or processed. The jaw mechanics reinforce this. The long snout increased the strike range, allowing the animal to lunge forward and intercept prey at a slightly greater distance than a shorter snouted animal could manage. The jaw muscles, based on the skull anatomy, were probably not especially powerful in terms of crushing force, but they would have been fast. A quick snap was more important than a powerful bite when the prey was a fish that could accelerate away in a fraction of a second. One of the most direct lines of evidence for what plesiosaurs actually ate comes not from teeth or jaw shape, but from stomach contents. Fossilized stomach contents are rare because soft tissue does not preserve easily, but they do exist for some plesiosaur specimens. Fish bones have been found in association with plesiosaur rib cages, sometimes in positions that suggest they were inside the body at the time of death. Cephalopod hooks, the small, hard, curved structures that squid and related animals have on their tentacles, have also been recovered from plesiosaur specimens. These hooks are small enough to preserve even when the soft tissue of the tentacles is long gone, and they turn up with enough regularity in plesiosaur-bearing deposits to suggest that cephalopods were a meaningful part of the diet. For Dolichorhynchops specifically, no stomach contents have been formally documented in the way that some other specimens have, but the broader picture from related polycotylids and from the tooth and jaw anatomy is consistent. Fish and soft cephalopods were the primary food source. The seaway had both in abundance. Among the fish, one name comes up repeatedly in discussions of the western interior seaway: Encodus. This was a medium-sized predatory fish, reaching roughly a metre or more in length in some specimens, with distinctive fang-like teeth that earned it the nickname the saber-toothed herring, which is a slightly alarming thing to imagine in your local waterway. Encodus was fast, abundant, and occupied a similar mid-level predator role among the fish that Dolichorhynchops occupied among the marine reptiles. It was also itself a pursuit predator, meaning it was not a slow or passive target. Catching Encodus would have required genuine speed and coordination. Other fish in the seaway included Chimolichthys, another fast-moving predatory species, and Bananogmius. a larger, deeper-bodied fish that would have represented a more substantial meal. The seaway was genuinely rich with fish life, and the fossil density in the Niobrara chalk confirms this. Fish remains are among the most common fossils in the formation, suggesting that the water above that ancient seafloor was teeming with activity. Cephalopods were also present in large numbers. Ammonites, with their coiled shells, are found throughout Niobrara deposits, though their hard shells make them less likely targets for Dolichorhynchops given the tooth design. Soft-bodied forms, the squid-like animals that left behind only their hooks, and occasionally their internal structures, would have been more accessible prey. Squid are fast, but they are also soft, and a quick grab with interlocking teeth would have been effective. Modern marine predators like dolphins and tuna regularly target squid, and there is no particular reason to think the seaway's polycotylids were any different in that regard. When we try to reconstruct how Dolichorhynchops actually hunted, we are working partly from anatomy, partly from analogy, and partly from the ecological logic of the environment it lived in. The body plan, as discussed at length, is consistent with active pursuit predation. But pursuit predation can take different forms. Some pursuit predators chase prey in open water over long distances, relying on endurance as much as speed. Others make short, explosive bursts from relatively close range, relying on acceleration and surprise to close the gap before the prey can fully respond. The body plan of Dolichorhynchops, with its large flippers and compact form, seems better suited to the second approach. The four-flipper system is powerful but probably not optimized for sustained long-distance cruising in the way that a dolphin's tail-driven locomotion is. Short, powerful bursts combined with maneuverability fits the mechanical picture better. A comparison to tuna is useful here, and not just because both animals are fast. Bluefin tuna are pursuit predators that use speed and acceleration to run down prey, often attacking from below or from the side in a way that limits the prey's escape options. They're also highly visual hunters, relying on sharp eyesight to track fast-moving targets in three-dimensional space. The visual component is important, and it brings up something interesting about Dolichorhynchops that is easy to overlook: the eye placement. In many plesiosaurs, the eyes are positioned on the sides of the skull, giving a wide field of view but limited binocular overlap in front. In Dolichorhynchops, the orbital position suggests a somewhat more forward-facing orientation than in some other plesiosaurs, which would have increased the zone of binocular vision in front of the snout. Binocular vision is valuable for depth perception, and depth perception is valuable for judging the precise distance and trajectory of a moving target. This is why pursuit predators in general tend to have more forward-facing eyes than prey animals, which benefit more from wide-angle vision to detect threats from any direction. The eye placement in Dolichorhynchops is not as extreme as in a cat or an owl, and the binocular overlap was probably limited compared to modern pursuit predators, but the trend in that direction is consistent with an animal that needed to accurately track and intercept moving prey rather than simply scan for threats across a wide arc. There is also the question of hunting depth. Dolichorhynchops was not constrained to the surface. As a reptile, it needed to breathe air, which means it would have made regular trips to the surface, but between breaths it was free to move through the water column. The seaway was not uniformly deep, and different depths would have offered different prey concentrations. Fish and squid tend to aggregate at certain depths depending on light levels, temperature, and prey availability. A predator that could move efficiently through different depth ranges had access to a more varied hunting ground than one confined to a narrow band of the water column. The dive behaviour of Dolichorhynchops is not something the fossil record can tell us directly, but there is no anatomical reason to think it was restricted to shallow water. The compact, streamlined body and powerful flippers would have been effective at depth as well as near the surface. Now, one of the more speculative but genuinely interesting questions about Dolichorhynchops concerns whether it ever hunted in groups. There is no direct fossil evidence for cooperative hunting behaviour. No deposit has been found where multiple individuals appear to have died together in circumstances suggesting coordinated activity. But there is something worth noting. In certain Niobrara localities, Dolichorhynchops specimens are found in relatively close proximity to one another. This clustering could reflect many things, including shared preferences for certain water conditions, the tendency of carcasses to drift together in current patterns, or simply the fact that productive fishing grounds attract multiple individuals. Some researchers have noted that the clustering is interesting enough to raise the question, without providing a clear answer. Modern marine predators like dolphins and some shark species do cooperate when hunting schooling fish, driving prey into tighter groups that are easier to pick off. Whether Dolichorhynchops had the social and cognitive machinery for anything like that is genuinely unknown. It is a possibility, not a conclusion, and the honest answer is that the fossil record has not yet given us enough to say more than that. What the fossil record does allow us to say is that this animal was a capable, well-adapted predator operating in one of the most productive marine environments of the Cretaceous. The seaway was not a gentle place. Every animal in it was under pressure, from the fish trying to avoid being eaten to the plesiosaurs trying to avoid the mosasaurs that could swallow them whole. In that context, the hunting ability of Dolichorhynchops was not just a matter of getting enough food. It was a survival mechanism in a more direct sense. An animal that could not hunt effectively would not have had the energy reserves to also evade predators, reproduce, and maintain the metabolic demands of an active lifestyle in warm, competitive water. There is something almost elegant about how the whole system fits together. The teeth designed for gripping slippery fish, the long snout for extending the strike range, the forward-leaning eye placement for tracking moving targets, the compact, powerful body for generating speed and burst acceleration, the 4 large flippers for maneuverability and thrust. Each of these features makes sense individually, but together they describe a coherent hunting machine, one that was specifically shaped by millions of years of selection pressure in an environment that rewarded speed, precision, and the ability to catch fast prey in open water. It is also worth pausing for a moment on what this animal was not. Dolichorhynchops was not an apex predator. It was not the largest or most dangerous animal in the seaway. The mosasaurs, particularly Tylosaurus, occupied a different tier entirely. Dolichorhynchops was a mid-level predator, efficient and specialized, but operating within a food web that included animals capable of eating it. The same speed and agility that made it effective at catching fish also served as its primary defense against larger predators. This dual function of locomotion, offense and defense simultaneously is a recurring theme in the ecology of medium-sized marine predators, and it shapes the life history of the animal in ways that go beyond simple hunting behavior. The hunting strategy of Dolichorhynchops, then, was not a single behavior, but a whole way of being in the water. Fast, visually oriented, targeting fish and soft-bodied prey, probably making short, high-speed bursts rather than sustained chases, operating across a range of depths, and doing all of this in an environment that demanded both efficiency and vigilance. The picture that emerges is not the dramatic, slow-motion battle of giant predators that sometimes dominates popular images of prehistoric oceans. It is something more like the daily, relentless, precise work of a highly capable hunter in a world full of both opportunity and danger. Understanding what Dolichorhynchops ate and how it hunted gives us the living animal in a way that anatomy alone cannot quite achieve. The skeleton tells us what it was capable of. The hunting behavior tells us what it actually did with those capabilities, day after day, in the warm, productive water of a sea that covered the heart of a continent. But to understand this animal fully, we also need to understand where the evidence for all of this comes from. And that means looking at the fossils themselves, where they were found, who found them, and what the circumstances of their discovery revealed about the world they came from. The story of how Dolichorhynchops came to be known to science begins, as so many paleontological stories do, in the chalk. Specifically, in the Niobrara chalk of western Kansas and Nebraska, a formation that has given paleontologists more remarkable fossils per square mile than almost anywhere else in North America. The Niobrara is not dramatic-looking terrain. It is open, rolling, windswept country, the kind of landscape that makes you feel small in a quiet way. The chalk itself is pale and soft, formed from the compressed remains of billions of tiny marine organisms that sank to the floor of the western interior seaway over millions of years. It weathers out of hillsides in great pale bluffs and exposures, and when it does, it sometimes brings bones with it. The chalk is an extraordinary preserving medium. Fine-grained and chemically stable, it encases fossils with a care that coarser sediments rarely manage. Bones come out of the Niobrara with their structure intact, sometimes with articulated skeletons still largely in place, the animal preserved more or less as it fell. The seaway floor was deep enough and calm enough in many places that carcasses settled without being torn apart by currents, and the fine chalk sediment buried them slowly, gently, and thoroughly. The result is a fossil record of unusual completeness, and Dolichorhynchops is one of its beneficiaries. The genus was formally described in 1902 by Samuel Wendell Williston, one of the most productive and methodical paleontologists working in North America at the turn of the 20th century. Williston had a long association with the Niobrara material. He had spent years working in Kansas, first as a student and assistant under O.C. Marsh at Yale, and later as a professor at the University of Kansas and then the University of Chicago. He knew the chalk intimately, and he had a particular gift for careful anatomical description, which is not as common a talent as one might hope in the history of fossil hunting. He named the new genus Dolichorhynchops, drawing from the Greek for long-snouted face, which is an accurate if not especially poetic name for an animal with a snout like that. The type species was named Dolichorhynchops osborni, in honour of Henry Fairfield Osborn, the influential American paleontologist who was at the time president of the American Museum of Natural History. Osborn was a significant figure in the scientific establishment of that era, and naming a species after a colleague or patron was standard practice, sometimes a genuine tribute, and sometimes a piece of professional diplomacy. In this case, it was probably both. The specimen Williston worked with came from the Niobrara exposures in the region that straddles western Kansas and southwestern Nebraska, a stretch of country that had already become famous in paleontological circles for the sheer density of remarkable fossils it produced. By 1902, the Niobrara had already yielded Elasmosaurus, the long-necked plesiosaur that Edward Drinker Cope had famously reconstructed with the head on the wrong end of the body in 1868, an error that became one of the more entertaining cautionary tales in the history of science. It had produced Tylosaurus, one of the largest mosasaurs ever found. It had given up Pteranodon specimens, the great toothless flying reptile with the long bony crest, and Xiphactinus, the large predatory fish sometimes called the bulldog fish, whose fossils occasionally preserve the remains of smaller fish still inside the stomach cavity, a kind of accidental last meal preserved in stone. The Niobrara was, in short, a remarkable place, and Williston knew it. The world of fossil hunting in the American West during the late 19th and early 20th centuries was not a calm or collegial one. The so-called bone wars between Cope and Marsh had defined the previous generation, a period of competitive fossil collecting so intense and personally bitter that it involved sabotage, bribery, stolen specimens, and accusations that followed both men to their graves. By Williston's time, that particular feud had cooled, mostly because both Cope and Marsh had died by 1899, but the competitive atmosphere they had cultivated did not simply disappear. Collectors still raced to find specimens, institutions still competed for prestige, and the Kansas chalk was a contested ground in more ways than one. Williston himself had worked for Marsh before breaking with him, and he was not above the politics of the field. But he was also a genuinely careful scientist, and his descriptions of the Niobrara material, including Dolichorhynchops, have held up well over the decades. What Williston had in that first described specimen was a reasonably complete skull and portions of the skeleton, enough to establish the genus clearly and to describe the most distinctive features of the animal. The long, narrow snout, the interlocking teeth, the short neck, conspicuously different from the elongated neck of Elasmosaurus, which had been found in the same formation and which loomed large in the popular imagination of prehistoric sea creatures. Williston recognised Dolichorhynchops as belonging to a different group, the short-necked polycotylids, and placed it accordingly within the broader classification of plesiosaurs. Over the following decades, additional specimens were recovered from the Niobrara and from related formations in neighbouring states. A second species, Dolichorhynchops herschelensis, was eventually described from material found in Saskatchewan, Canada, extending the known range of the genus northward and providing additional data on the variation within the group. The herschelensis specimens are somewhat larger than the Kansas material, and there are subtle differences in skull proportions and tooth count, enough to justify the separate species designation, while still clearly placing the animal within the same genus. The Canadian material came from the Bear Paw Formation, a marine deposit roughly equivalent in age to the Niobrara, laid down in the same vast inland sea from a different geographical position. The accumulation of multiple specimens over time is what elevates Dolichorhynchops from an interesting curiosity to a genuinely well-understood animal. Many prehistoric marine reptiles are known from a single fragmentary skull, or a handful of vertebrae, or an isolated flipper bone that tells us the animal existed but very little about what it was actually like. Dolichorhynchops is comparatively well represented. There are enough specimens to give researchers a sense of individual variation, growth stages, and the range of body sizes within the species. There are skulls complete enough to study the teeth in detail, limb bones complete enough to model the flipper mechanics, and body proportions well enough preserved to build reasonable reconstructions of the living animal. This is not a given in paleontology. It is a gift, and one that the Niobrara chalk has provided more generously for this animal than the fossil record typically allows. It is worth saying something about what the process of finding these specimens actually looked like, because it was not a matter of walking across a field and spotting a skeleton. The Niobrara exposures are weathered by wind and rain, and fossils erode out of the chalk over time. A bone might appear at the surface as a small, pale fragment, easily mistaken for a piece of chalk itself, unless you know what you're looking for. Experienced collectors learn to read the chalk, to notice the slight colour and texture differences that indicated bone rather than matrix, and to follow a fragment back into the hillside to find what lay beneath. The work was slow, physical, and often frustrating. Summer in western Kansas is genuinely hot. The landscape offers little shade, and the chalk dust gets into everything. The romantic image of fossil hunting does not always survive contact with the actual conditions. Once a specimen was located and its extent was understood, the extraction process required careful work with hand tools, consolidants to stabilize fragile bone, and plaster jackets to protect the material during transport. In the early 20th century, the technology was more limited than it is today, and some specimens were inevitably damaged during collection or preparation. The fact that as much good material survived as it did is a testament to the care of the collectors who worked the Niobrara through that period, even in conditions that were far from ideal. The Niobrara was also not the exclusive province of professional scientists. Local ranchers and farmers occasionally found bones on their land and sometimes contacted universities or museums. Some of the most significant specimens in various collections were initially spotted by people who were not paleontologists, but who recognized that what they had found was worth reporting. This kind of informal network of local knowledge was important in the early decades of Niobrara research, and it is still relevant today. The chalk continues to weather, and new material continues to come to the surface. The formation has not been exhausted. By the mid-20th century, Dolichorhynchops had been established firmly enough in the literature that it appeared in textbooks and popular natural history accounts as a representative short-necked plesiosaur of the Cretaceous. Its name was not as widely known as Elasmosaurus or Tylosaurus, the more dramatic-looking animals from the same formation, but among researchers working on plesiosaur systematics and ecology, it was a well-regarded and frequently referenced taxon. The quality and quantity of the specimens made it a useful anchor point for comparisons with other polycotylids, and Williston's original descriptions, supplemented by later revisions, provided a solid foundation for subsequent work. There is something quietly satisfying about the way the Niobrara material accumulated over the decades. Each new specimen added a small piece to the picture. A better preserved skull here, a more complete set of limb bones there, a specimen from a slightly different stratigraphic level that told researchers something about the time range of the animal. The fossil record is rarely generous in the way we might wish, but for Dolichorhynchops it was generous enough that the animal can be discussed with a degree of confidence that many prehistoric creatures simply do not allow. We can say what it looked like with reasonable certainty. We can say what it ate. We can say how it moved. We can place it in its ecosystem and describe its relationships with the other animals around it. All of this rests on the physical evidence that the chalk preserved and that generations of collectors and researchers extracted, studied, and described. The Niobrara itself as a place deserves a moment of appreciation. It is not a famous landscape in the way that the Badlands of South Dakota or the Grand Canyon are famous. It does not draw crowds or appear on many travel posters, but for anyone interested in the deep history of life on this continent, it is one of the most extraordinary places in North America. The chalk bluffs of western Kansas contain, in compressed and mineralized form, a complete snapshot of an ecosystem that existed 85 million years ago. The fish, the sharks, the mosasaurs, the plesiosaurs, the flying reptiles, the diving birds, the ammonites, all of them are there in the rock waiting to be found. Dolichorhynchops is one of the clearest windows into that world, and the clarity of that window is due in no small part to the preserving qualities of the formation in which it was buried. What makes the discovery history of this animal particularly interesting is not just the accumulation of specimens over time, but what those specimens began to reveal when researchers looked at them more carefully. Anatomy and taxonomy are one layer of the story, but bones sometimes preserve evidence of things that happened during the animal's lifetime, events that left marks in the skeleton, traces of behaviour, injury, survival, and biology that go beyond simple classification. And in the case of the polycotylids, the Niobrara material eventually produced something that nobody had expected, something that changed the way scientists understood not just this group of animals, but the reproductive biology of plesiosaurs as a whole. That unexpected thing came from a specimen that was not technically Dolichorhynchops itself, but from its closest family. A polycotylid, same group, same body plan, same general way of moving through the water. And what it showed, preserved inside the rock after 83 million years, was something so specific and so intimate that it genuinely stopped researchers in their tracks when the full picture became clear. The specimen in question is catalogued as LACM1682, held in the collections of the Natural History Museum of Los Angeles County. It belongs to a species called Polycotylus latipinnis, a North American polycotylid that shared the western interior seaway with Dolichorhynchops and occupied a very similar ecological space. The specimen had been known for some time before its most remarkable feature was fully understood. When Robin O'Keefe of Marshall University and Luis Chiappe of the Natural History Museum of Los Angeles County examined it carefully and published their findings in the journal Science in 2011, the paleontological community paid close attention. What they described was a large adult polycotylus with, preserved within its body cavity, the partial skeleton of a single fetus. A near-term fetus, large relative to the adult, positioned in a way that was consistent with it having been inside the body of the living animal at the time of death. This was not a small fish that the adult had swallowed. The proportions were wrong for that, and the position was wrong for that. The fetal skeleton was identifiable as a juvenile polycotylus, with the same body plan, the same flipper structure, the same general anatomy as the adult. It was, in the clearest possible terms, an unborn offspring. And what that meant was significant in a way that extended far beyond this single specimen. It meant that plesiosaurs gave live birth. This had been suspected by some researchers for a number of years before 2011. The logic was reasonable. Plesiosaurs had large, rigid bodies with 4 flippers and no obvious ability to haul themselves onto land in the way that sea turtles do. Their limb structure was so thoroughly adapted to aquatic life that terrestrial movement would have been, at best, extremely difficult and probably impossible for the larger species. Sea turtles manage it, but they have a very different body plan. Plesiosaurs did not have the flexible, weight-bearing limbs needed to dig a nest on a beach. Some researchers had therefore proposed that live birth was the most likely reproductive strategy, but without direct fossil evidence, it remained an inference rather than a fact. LACM 1682 turned that inference into evidence. Not just any evidence, but the kind of clean, unambiguous physical evidence that paleontology rarely provides for questions of soft tissue biology and behaviour. Here was the fetus, inside the adult, in a species closely related to Dolichorhynchops. The conclusion was not speculative, it was written in bone. There was something else about the specimen that O'Keefe and Chiappe noted, and this is where the finding becomes even more interesting. The fetus was large. Relative to the adult, it was proportionally much bigger than the offspring of most reptiles, which tend to produce many small eggs. A large crocodile, for example, lays dozens of eggs, each containing a relatively small hatchling. The strategy is quantity. Lose most of them to predators, and enough survive to continue the lineage. But the polycotylus fetus was not small. It was well developed, probably close to birth, and represented a significant investment by the adult. O'Keefe and Chiappe estimated that the fetus was roughly 1/3 the length of the adult. That is not a small egg. That is a substantial offspring, one that required considerable resources to produce. This matters because of what it implies about behaviour. In the modern world, the animals that invest heavily in single, large offspring tend to be the ones that also invest in parental care after birth. The comparison that comes to mind most immediately is cetaceans, whales and dolphins, which give birth to single, large calves and then nurse and protect them for extended periods. Elephant seals do something similar. Even some sharks, which give live birth to relatively large pups, show behaviours that reduce the risk to offspring immediately after birth. The general principle is that if you are going to put a large amount of energy into producing one offspring rather than many small ones, it makes sense to protect that investment after birth, rather than simply releasing the newborn into the water and hoping for the best. O'Keefe and Chiappe were careful not to overclaim. They did not say that plesiosaurs definitely formed family groups or nursed their young in the way that dolphins do. The fossil record cannot show that level of behavioural detail from a single specimen. What they said was that the large offspring size was consistent with a K-selected reproductive strategy, the biological term for the approach that emphasises quality over quantity, and that this in turn was consistent with some degree of post-birth parental care. Not proven, consistent with. That is the appropriate level of confidence for a conclusion drawn from one fossil, however remarkable. But the implication is there, and it is worth sitting with for a moment. If polycotylids gave birth to large, well-developed single offspring, and if the energetic logic of that strategy points towards some form of parental investment after birth, then these animals were not simply solitary hunting machines moving through the seaway in isolation. They may have travelled in small groups at times. Adults may have stayed near their young for a period after birth, at least long enough to give the newborn a better chance of surviving the first vulnerable days or weeks of life. The Western Interior Seaway was not a forgiving place for a small newly born animal. Mosasaurs, large sharks and other predators were everywhere. A young polycotylid on its own from the moment of birth would have faced very long odds. This connects back to Dolichorhynchops directly, because Dolichorhynchops was a polycotylid. It belonged to the same family as Polycotylus latipinus. The shared body plan, the shared ecological context, the shared phylogenetic position all make it essentially certain that Dolichorhynchops reproduced in the same way. It gave live birth, it probably produced single, large, well-developed offspring. And it may have exhibited some form of protective behaviour toward its young, at least in the immediate period after birth. This changes the mental image of the animal in a quiet but meaningful way. A fast-moving pursuit predator in an inland sea is one kind of picture. An animal that also gave birth to living young, that carried a single large fetus through the water as it hunted, that may have stayed close to its offspring in the days after birth, is something richer and more complex. It is still a predator. It is still built for speed. But it is also an animal with a life history, with biological investments and vulnerabilities, with a set of behavioural imperatives that went beyond simply finding the next meal. The vulnerability that pregnancy creates is worth considering. A female Dolichorhynchops in the late stages of carrying a near-term fetus would have been heavier, possibly somewhat slower, and certainly more physiologically stressed than at other times in her life cycle. The same seaway that she navigated efficiently when not pregnant would have presented different challenges during that period. The apex predators of the seaway, the large Mosasaurs in particular, did not reduce their activity because a polycotylid happened to be pregnant. The pressure was constant. Whatever behavioural adjustments a pregnant Dolichorhynchops might have made, whether staying in shallower water, remaining closer to others of its kind, or altering its hunting range, those adjustments would have been shaped by the same ecological pressures that shaped every other aspect of its life. There is also the question of where birth happened. Sea turtles return to beaches, dolphins give birth in open water, whales sometimes seek sheltered bays. For Dolichorhynchops, with its fully aquatic body plan and apparent inability to come ashore, birth would have been an entirely aquatic event. The newborn would have entered the water directly, presumably already capable of swimming, as is typical for large-brained, well-developed offspring in marine mammals. The parallel with cetacean calves, which are born tail first and swim almost immediately, is not a perfect analogy, because plesiosaurs and cetaceans are not closely related, but the physical logic is similar. A large, well-developed offspring born into the water has a better chance of immediate survival than a small, underdeveloped one. The 2011 paper by O'Keefe and Chiappe has held up well in the years since its publication. It has been cited extensively and has not been seriously challenged on its core conclusions. The identification of the fetal material as a juvenile polycotylid rather than stomach contents is considered solid, based on the position of the bones, the presence of plesiosaur-specific skeletal features, and the size and proportions of the material. It remains one of the most important single specimens in plesiosaur research, not because it is the largest or most complete plesiosaur ever found, but because of what it reveals about a biological process that left almost no other trace in the fossil record. It is worth noting, too, that this kind of discovery is only possible because of the quality of preservation in the Niobrara and related chalk formations. A fetal skeleton inside an adult is a fragile thing. The bones are small, not yet fully mineralized, easy to disarticulate and scatter during decomposition. For them to be preserved in place, within the body cavity of the adult, the burial conditions had to be right. The animal had to sink to the seafloor quickly enough after death that the fetal skeleton was not disturbed before sediment covered it. The fine-grained chalk that accumulated on the seaway floor was exactly the kind of sediment that could achieve this, settling slowly and gently over a carcass, filling spaces, and holding bones in place over millions of years. The Niobrara, again, was doing what it does best. For anyone who has spent time thinking about these animals as living things rather than as taxonomic categories, the pregnant specimen carries a particular kind of weight. It is not just a data point, it is a moment. An animal that was alive, that was carrying new life, that died in the sea it called home, and that sank to the bottom and was covered by chalk and time and eventually became a window into something we had not known before. The science is what matters, and the science is solid. But the human response to that science, the quiet recognition that this was a living creature with a biology as complex and as vulnerable as any modern animal, is not something to be dismissed. It is part of what makes paleontology worth doing. What the pregnant Polycotylus specimen did, beyond its specific scientific contributions, was remind researchers that these animals had full biological lives. They were not simply swimming skeletons. They reproduced. They were vulnerable. They invested in their offspring. They faced the seaway not just as hunters, but as animals with life histories that included risk, dependency, and care. That fuller picture, applied to Dolichorhynchops by reasonable extension, makes the animal more interesting to study and more meaningful to understand. And if reproduction was one window into the behavioural life of these animals, the bones themselves offered another kind of evidence entirely. Not evidence of birth, but evidence of survival. Evidence that some individuals had faced violence, had been injured, and had lived long enough afterward for the damage to heal. The skeletons of animals from the Western Interior Seaway sometimes carry marks that were not made by the process of fossilization, but by the teeth and jaws of other creatures that were alive at the same time. Those marks, when they appear on healed bone, tell a story that is different from anything a complete undamaged skeleton can offer. They tell the story of an encounter that didn't end in death, of an animal that was attacked and survived, and of what that survival meant in the context of a sea that was never, for a single moment, safe. Healed bone is one of the quieter revelations in paleontology. It does not announce itself the way a complete skeleton does. It does not fill a museum hall or appear on the cover of a journal with a dramatic reconstruction behind it. It is a small thing, sometimes just a roughened surface, a thickened edge, a callus of new bone laid down over an old wound. But what it represents is significant in a way that takes a moment to appreciate. A healed injury means the animal lived. It means the attack happened. The wound was serious enough to leave a mark on the skeleton, and yet the animal survived long enough for its own biology to respond, to begin repairing the damage, to lay down new material over the site of trauma. In a sea as dangerous as the Western Interior Seaway, that kind of survival was not guaranteed, it was earned. Bite marks on marine reptile bones from the Niobrara chalk have been documented across multiple specimens and multiple species. They appear on ribs, on limb bones, on vertebrae, and occasionally on skull material. Some of them are clean, sharp, and unhealed, the marks of a predator feeding on a carcass after death. Others show something different. The bone around the wound has been remodelled. New material is formed. The surface has a different texture from the surrounding area, one that tells researchers this animal was alive when the injury occurred, and remained alive for some time afterward. These healed injuries are not common, but they are not vanishingly rare either. They show up often enough in Niobrara material that researchers have been able to study them systematically and draw some conclusions about the identity of the attackers. Two main candidates emerge from the bite mark evidence. The first is Mosasaurs. The large mosasaurs of the seaway, particularly Tylosaurus, had broad, powerful jaws and robust conical teeth, capable of inflicting serious damage on bone. Mosasaur bite marks tend to be large, deep, and widely spaced, reflecting the size of the animal delivering them. The second candidate is sharks, and among sharks, Squalicorax deserves particular attention. Squalicorax was a medium-sized shark, roughly 3 to 5 meters long, that was extremely common in the Western Interior Seaway. It is sometimes called the crow shark, and it appears in the fossil record with remarkable frequency. Its teeth are serrated and recurved, well suited to cutting through flesh and bone alike. Squalicorax bite marks have been identified on the bones of fish, mosasaurs and plesiosaurs from the Niobrara, and some of those marks appear on bones that show evidence of healing. This is a detail worth pausing on. A shark bite that heals means the plesiosaur was bitten, escaped, and lived. That is not a small thing in a sea where Squalicorax was one of the most abundant predatory animals. One documented case that receives attention in the literature involves plesiosaur material from the Niobrara, showing tooth marks consistent with Squalocorax, with bone remodelling indicating survival. The specifics of individual specimens can be difficult to track across older literature because specimen assignments and identifications have shifted over the decades, but the broader pattern is consistent. Plesiosaurs in this formation were bitten by sharks, and some of them survived. The evidence is there in the bone itself, written in the language of healing tissue. What this tells us about the life of Dolichorhynchops is indirect but meaningful. Squalocorax was not typically an apex predator in the sense that Tylosaurus was. It was opportunistic, a scavenger and an ambush feeder, capable of attacking injured or vulnerable prey, but not consistently targeting healthy, fast-moving animals at the top of their form. A Squalocorax bite on a plesiosaur might reflect an attack on a resting animal, a sick one, a juvenile, or one that was already injured. It might also reflect a failed attack on a healthy individual, one that was fast enough or agile enough to escape after the initial contact. The healed bite mark does not tell us which scenario applies. It tells us only that the animal survived, and that is already more than most fossils reveal. The mosasaur question is different in scale and in kind. Tylosaurus periga, the largest mosasaur known from the Niobrara, was a genuinely formidable animal. Estimates of its length range from about 12 to 13 metres for the largest individuals, though most adults were probably somewhat smaller. Even at 10 metres, it was a substantially larger animal than Dolichorhynchops, which topped out at around 5 metres in the biggest specimens. The size difference alone makes the dynamic between these two animals worth thinking about. Dolichorhynchops was not competing with Tylosaurus. It was potential prey. Tylosaurus had a long, robust skull, a powerful tail, and a body plan built for ambush and pursuit in roughly equal measure. Its teeth were large and conical, not serrated like a shark's, but capable of gripping and crushing. Its jaw mechanics were not designed for slicing, but for seizing and holding. An attack by Tylosaurus on a smaller plesiosaur would have been an overwhelmingly physical event, a matter of mass and grip rather than surgical precision. A Dolichorhynchops caught by a Tylosaurus would have had limited options. The size differential made direct resistance unlikely to succeed. The only real answer was not to be caught in the first place. This is where the speed and agility of Dolichorhynchops becomes relevant not just as a hunting tool but as a survival mechanism. The same body plan that made it effective at pursuing fish, the streamlined torso, the powerful flippers, the reduced drag from the short neck also made it harder to catch. A mosasaur relies heavily on its tail for propulsion, using an undulating body motion to generate thrust. This gives it strong straight-line speed over short distances, particularly in an ambush scenario. But turning, accelerating from rest, and making rapid directional changes are more difficult for an animal whose locomotion is dominated by lateral body flexion. A plesiosaur using foreflipper underwater flight can potentially generate more responsive maneuverability, the ability to change direction quickly without losing all forward momentum. Whether Dolichorhynchops was actually more maneuverable than Tylosaurus in a direct encounter is not something the fossil record can confirm with certainty. But the biomechanical logic is at least suggestive. There are documented cases of mosasaur bite marks on plesiosaur material from the Niobrara, and some of these too show signs of healing. One of the more frequently referenced examples involves a plesiosaur flipper bone, with deep parallel grooves consistent with large mosasaur teeth, surrounded by bone that has clearly been remodelled in response to the wound. The animal was bitten on the flipper, which is a particularly interesting location. A damaged flipper would have compromised swimming ability directly. For an animal whose survival depended on speed and maneuverability, an injured flipper was not a minor inconvenience. It was a serious threat to its ability to hunt, to escape future attacks, and to function normally in the seaway, and yet the bone healed. The animal continued living. Whether it recovered its full swimming performance is unknown, but it survived the immediate aftermath of the attack long enough for the bone to respond. This kind of evidence accumulates into something larger than any individual specimen. It builds a picture of the seaway as a place of ongoing, repeated and sometimes survived violence. Animals were attacked regularly. Some died immediately. Some died later from their wounds. And some, perhaps more than we might expect, survived and continued. The seaway was not a place where predation was a rare or catastrophic event. It was continuous background pressure, a constant feature of daily existence for every animal that swam through it. For Dolichorhynchops specifically, this pressure would have shaped behaviour in ways that are difficult to reconstruct, but not impossible to reason about. Animals that face consistent predation pressure from larger predators tend to develop behavioural responses to that pressure. They may alter their depth range, spending more time in water that is shallow enough to make large mosasaur ambushes less effective. They may alter their activity timing, being more active at certain times of day when visibility conditions favour their own detection of threats. They may remain in groups, where multiple sets of eyes reduce the likelihood that a predator can approach undetected. None of these behaviours leave direct traces in the fossil record, but they are consistent with what we know about modern animals facing similar ecological pressures. The clustering of Dolichorhynchops specimens in certain Niobrara localities has been noted by researchers, though interpreting such clustering is always cautious work. Fossil accumulations can result from many things: a catastrophic event, a local food source that attracted multiple individuals, a preferred habitat that was used repeatedly over time, or simply favourable preservation conditions in a particular area. The clustering does not prove group behaviour, but it does not rule it out either. For an animal facing the predator community of the western interior seaway, group behaviour would have made sense, and the depositional record at least does not contradict the possibility. It is also worth considering what healed injuries tell us about the age and longevity of these animals. A healed injury requires time. The bone remodelling process is not instantaneous. Depending on the severity of the wound and the metabolic rate of the animal, significant healing might take weeks or months. An animal with multiple healed injuries, or with injuries that show extensive remodelling, was almost certainly not a young juvenile. It was an animal that had been living in the seaway for some time, accumulating a history of encounters. This is a small thing, but it is meaningful. It suggests that individual Dolichorhynchops could survive to a meaningful age in the seaway, navigating its dangers not just by luck, but by whatever combination of speed, awareness, and behavioural flexibility they had available to them. The relationship between Dolichorhynchops and the predators that threatened it was not a simple, one-way dynamic. Dolichorhynchops was itself a predator, and a capable one, but it existed within a hierarchy that it could not dominate. It was faster than many things and slower than some. It was more manoeuvrable than the largest mosasaurs and more vulnerable than the smallest fish. Its position in the seaway was defined by this middle ground, and the evidence of injury and healing in the fossil record is one of the clearest expressions of what that middle ground actually felt like in practice. Not safe. Not helpless. Something in between, navigated daily. The Niobrara chalk preserves this reality with unusual fidelity. Most fossil sites give us bones, and from bones we reconstruct anatomy. The Niobrara gives us bones that carry the marks of living, of being bitten and surviving, of moving through a world that was actively trying to consume you. That is a different kind of information, and it is one of the reasons the Niobrara material remains so valuable to researchers studying the behaviour and ecology of late Cretaceous marine animals. The bones are not just structural records, they are biographical ones, and so the picture of Dolichorhynchops that emerges from all of this is richer than a simple description of anatomy and speed would suggest. It was fast, yes. It was a pursuit predator, almost certainly. It gave live birth, by strong inference from its close relatives. It was targeted by sharks and mosasaurs, and some individuals survived those encounters. It lived in one of the most biologically productive and ecologically dangerous marine environments of the Mesozoic, and it was shaped by that environment in every aspect of its biology, from the streamlined body that let it chase prey to the reproductive strategy that produced well-developed offspring capable of surviving from the moment of birth. The injury evidence, modest in volume but significant in implication, adds one more layer to that picture. It confirms that these were not animals moving through the seaway in a kind of frictionless ease, untouched by the violence around them. They were participants in it, sometimes the hunter, sometimes the hunted, sometimes the survivor of something that could have ended them. The healed bone is proof of that survival, quiet and specific and real in a way that reconstructions and estimates can never quite be. What shaped Dolichorhynchops, then, was not just the fish it chased or the flippers it used to chase them. It was the whole web of relationships it existed within, the predators above it, the prey below it, the competitors alongside it, and the physical environment that structured all of those interactions. Understanding that web is the next step in understanding the animal itself. The seaway was not just a backdrop, it was an active system, and Dolichorhynchops was one functioning part of a much larger whole. So let us try to map that web more carefully, because Dolichorhynchops did not exist in isolation. No animal does. Every creature in an ecosystem is connected to others through feeding relationships, competition, shared habitat, and the cascading effects that ripple outward whenever any one part of the system changes. The Western Interior Seaway was a particularly rich and well-documented example of a Cretaceous marine ecosystem, and the fossil record from the Niobrara chalk is dense enough that researchers have been able to reconstruct its food web with more confidence than is possible for most prehistoric environments. What emerges from that reconstruction is a picture of an ecosystem that was layered, dynamic, and full of animals occupying very specific roles. At the base of the system, as always, was primary production. Phytoplankton and other microscopic organisms formed the foundation, supporting vast quantities of small invertebrates and fish. The seaway was shallow enough in many areas to allow significant light penetration, which would have supported productive surface waters. This productivity cascaded upward through the food web. Small fish fed on invertebrates, larger fish fed on smaller fish. And the animals we tend to focus on, the plesiosaurs, mosasaurs and sharks, sat near the top of that cascade, feeding on the fish and cephalopods that the productive lower levels supported. Dolichorhynchops occupied what ecologists would describe as a mesopredator position. It was not at the apex of the food web, it was not the largest or most powerful predator in the seaway. But it was a genuine predator, not a filter feeder or a bottom grazer, and it occupied a specific functional role that the ecosystem depended on. Mesopredators are important in any food web because they help regulate the populations of the animals below them. Too many fish of a certain species, and the prey those fish depend on can collapse. A healthy population of mid-level predators keeps those populations in check, and the whole system stays in balance. Dolichorhynchops, along with other polycotylids like Trinacromerum and various sharks and large bony fish, would have performed that function in the seaway. The prey available to Dolichorhynchops was considerable. Encodus is perhaps the most frequently discussed, a fast-moving predatory fish that itself sat in the middle of the food web and was abundant enough in the Niobrara deposits to have earned the informal nickname the saber-tooth herring, a name that is admittedly a bit dramatic but does capture something real about the animal. Encodus had large, prominent fangs at the front of its jaws, and it was itself a pursuit predator of smaller fish. It ranged in size from relatively small to around 1.5 meters in some estimates, and its abundance in Niobrara sediments suggests it was one of the dominant mid-water fish in the seaway. For Dolichorhynchops, a fast-swimming, manoeuvrable fish like Encodus would have been a natural prey target, one that required speed and precision to catch. There was also Chimolishthis, another bony fish from the seaway, somewhat deeper bodied than Encodus, and probably occupying a slightly different part of the water column, and Bananogmius, a large, deep-bodied fish that could reach lengths of around 1.5 meters. with a body shape that suggests it was not particularly fast but may have been more nutritionally substantial. Catching a slower, larger fish requires different tactics than catching a fast, agile one, and it is worth considering that Dolichorhynchops may have targeted different prey species depending on availability and circumstance. Predators are rarely locked into a single prey type when options exist. Cephalopods also featured prominently in the seaway. Ammonites were abundant, their coiled shells preserved in enormous numbers in Niobrara sediments. Whether Dolichorhynchops actively targeted ammonites is less certain. The shells would have provided some protection, and the teeth of Dolichorhynchops were better suited to gripping slippery fish than to crushing hard shells. But soft-bodied cephalopods, things like squid and nautiloid-like forms without heavy external shells, would have been entirely accessible. Cephalopod hooks, the small curved structures from the arms of squid-like animals, have been found in association with plesiosaur specimens from related animals, suggesting that soft-bodied cephalopods were a regular part of the diet. They are energy-rich, relatively soft, and in some environments extremely abundant. For a pursuit predator like Dolichorhynchops, a dense aggregation of soft-bodied squid in the midwater would have been an efficient feeding opportunity. Above Dolichorhynchops in the food web, the picture becomes considerably more intimidating. Tylosaurus proriger, the largest mosasaur known from the Niobrara, reached lengths of 12 to 13 metres in the largest specimens. To put that in practical terms, that is roughly the length of a standard school bus. Tylosaurus was not a particularly fast animal by the standards of pursuit predators, but it was powerful, well-armoured, in the sense of having a robust skull and strong jaws, and almost certainly an ambush or opportunistic predator capable of taking large prey. For Dolichorhynchops, an encounter with a fully grown Tylosaurus would have been potentially fatal, and the speed and agility that made Dolichorhynchops an effective hunter would have been its primary defence. Platecarpus and Clydastes were smaller mosasaurs also present in the seaway, more agile than Tylosaurus and potentially more direct competitors with Dolichorhynchops for some prey items, as well as possible predators of smaller or younger Dolichorhynchops individuals. Mosasaur diversity in the Niobrara was substantial, and different mosasaur species likely occupied somewhat different ecological niches, reducing direct competition while still collectively maintaining pressure on animals at lower levels of the food web. The sharks deserve mention here as well. Squalochrax, sometimes called the crow shark, was a mid-sized predatory shark present in the seaway throughout much of its history. It reached lengths of perhaps 3 to 5 metres and appears to have been an opportunistic feeder, with bite marks attributed to Squalochrax found on a remarkable variety of Niobrara specimens, including fish, marine reptiles, and even terrestrial animals that ended up in the water. Squalochrax bite marks have been documented on plesiosaur bones, and some of those marks show signs of healing, meaning the plesiosaurs survived the encounter. Whether Squalochrax actively hunted Dolichorhynchops, or more commonly scavenged carcasses, is debated, but either way, it was a presence in the seaway that Dolichorhynchops would have shared its environment with throughout its existence. Cretoxyrhina, sometimes called the Ginsu shark, was larger and more formidable, reaching perhaps 6 or 7 metres. It was a more powerful predator than Squalochrax, and is thought to have been capable of taking large prey actively, including marine reptiles. Cretoxyrhina teeth and bite marks have been found on mosasaur and plesiosaur remains, suggesting it was not simply a scavenger, but a genuine apex predator in its own right, at least for part of the seaway's history. What is interesting about this layered community of predators is what it implies about how Dolichorhynchops would have had to navigate its world. It was not competing only with other plesiosaurs. It was competing with sharks, with smaller mosasaurs, with large bony fish like Zephactinus, which could reach lengths of 5 or 6 metres and was itself an aggressive pursuit predator. The seaway was not a place where any single lineage had a monopoly on a given food source. Multiple different animal groups were all converging on similar prey from different directions, using different body plans and different strategies. This kind of competitive pressure tends to drive ecological specialization, pushing animals toward the specific prey types and specific parts of the water column where they are most effective and face the least direct competition from others. For Dolichorhynchops, the specialization seems to have been toward fast mid-water fish in the open seaway. Its body plan, its teeth, its likely swimming performance all point toward an animal that was most effective in open water, pursuing prey at speed over short to medium distances. This is a different niche from a bottom-feeding shark, a different niche from an ambush predator lurking near the seafloor, and a different niche from a large mosasaur patrolling the surface. The seaway was large enough and productive enough to support all of these strategies simultaneously, and the fossil record shows us all of them preserved in the same formation. The sheer abundance of life in the seaway, as reflected in the fossil density of the Niobrara chalk, is worth pausing on for a moment. The Niobrara is not just a site where fossils occasionally turn up. It is a site where fossils are dense, where multiple complete or near-complete specimens of large marine animals have been recovered, where the record of an entire marine ecosystem is preserved in unusual detail. This density reflects the productivity of the seaway in life and the specific depositional conditions of the Niobrara seafloor in death. The fine-grained chalk accumulated slowly and steadily, burying carcasses before scavengers could fully disarticulate them, preserving skeletal associations and sometimes stomach contents that would be lost in more energetic depositional environments. The Niobrara is, in a sense, a slow-motion record of the seaway's daily business, accumulated over millions of years of deposition. That record also shows us how the seaway changed over time. The western interior seaway was not a static body of water. It expanded and contracted over its roughly 30 million year history, responding to global sea level changes in the tectonics of the North American continent. During the Campanian stage, when Dolichorhynchops was most abundant, the seaway was at or near its maximum extent, covering an enormous area and supporting the diverse community of animals we have been discussing. But around 70 million years ago, things began to change. The Laramide orogeny, the tectonic event responsible for building the Rocky Mountains, began to uplift the western interior of North America. As the land rose, the seaway began to drain. It did not happen overnight. It was a gradual process, measured in millions of years, but the direction was clear. The shallow inland sea that had dominated the centre of the continent for so long was retreating. As the seaway shallowed and fragmented, the ecosystem it supported began to unravel. Habitat area decreased. The connectivity between different parts of the seaway diminished. Prey population shifted as the physical environment changed. For animals like Dolichorhynchops, which were specifically adapted to the conditions of the open seaway, this environmental change would have been deeply destabilizing. The specialization that made them effective hunters in a stable, productive inland sea became a liability when that sea began to disappear. There was nowhere else to go that offered the same conditions, no adjacent habitat that replicated the seaway's particular combination of depth, temperature, productivity, and geographic extent. This is a pattern that recurs throughout the history of life. Specialization is a successful strategy in stable environments. It allows an animal to become very good at a specific thing, to extract resources efficiently from a particular ecological niche, to compete effectively against generalists that spread their energy across multiple strategies. But specialization carries a cost. It reduces flexibility. An animal that is exquisitely adapted to one set of conditions is poorly positioned to cope when those conditions change. The generalists, the animals that can eat a wider range of prey, tolerate a wider range of conditions, reproduce in a wider range of circumstances, tend to outlast the specialists when environments shift. The decline of Dolichorhynchops and the polycotylids more broadly through the late Campanian and into the Maastrichtian fits this pattern well. They were not outcompeted in a direct sense. They were not replaced by a better version of themselves. They were undermined by the disappearance of the world they had been built for. the seaway that had shaped every aspect of their biology, from the streamlined body that reduced drag in open water to the live birth reproductive strategy that produced offspring capable of surviving in a productive but dangerous environment, was ceasing to exist, and without it, they had no footing. The Mosasaurs and the long-necked elasmosaurids persisted somewhat longer, likely because they were either more ecologically flexible or because the remaining patches of marine habitat in the Late Cretaceous still offered them enough of what they needed. But the end Cretaceous extinction event 66 million years ago finished what the Laramide orogeny had started, removing the remaining marine reptiles from the world entirely, and leaving the oceans to be inherited by the lineages that would eventually produce modern whales, dolphins, and sea turtles. For Dolichorhynchops, the story ends earlier and more quietly, not in a single catastrophic moment, but in a gradual thinning of the seaway, a slow reduction of the world it depended on, until there was simply not enough of that world left to sustain it. The last Dolichorhynchops, wherever and whenever it lived, would not have known it was the last. It would have been doing what it always did, moving through the water column in pursuit of fish, navigating the same pressures that every generation before it had navigated. But the system around it was contracting, and eventually the contracting reached a point of no return. What this tells us about the ecology of the seaway is something worth carrying forward into the next question, which is not about the ecology of the animal, but about its place in the larger story of plesiosaur evolution. Because Dolichorhynchops was not just an animal in an ecosystem, it was a point on a family tree connected to other animals across time and geography, and understanding where it sits on that tree turns out to be more complicated than it might initially seem. So let us follow that thread a little further. The question of where Dolichorhynchops actually sits in the plesiosaur family tree is one that has occupied paleontologists for well over a century, and it is still not entirely resolved. That might sound surprising given how many specimens we have, but the classification of plesiosaurs has always been more complicated than it looks from the outside, and the short-necked forms like Dolichorhynchops sit right at the heart of some of the most persistent debates in the field. To understand why, it helps to start with the broad picture. Plesiosauria is the order that contains all of these animals. Within that order, the traditional division was fairly intuitive. There were the long-necked forms, small-headed animals with enormous numbers of neck vertebrae and relatively modest skulls, and there were the short-necked forms, animals with large heads, shorter necks, and more powerful jaw structures. The long-necked animals were called plesiosaurs, informally, and the short-necked animals were called pliosaurs. It was a clean and satisfying distinction, the kind that looks very tidy in a textbook diagram. The problem is that nature does not always cooperate with textbook diagrams. As more specimens were described and more rigorous cladistic analyses were applied, it became increasingly clear that the pliosaur-plesiosaur split was not as clean as it appeared. Some short-necked animals turned out not to be closely related to the large-headed apex predators like Leopleurodon or Kronosaurus at all. They had arrived at a similar body shape through a different evolutionary path. Dolichorhynchops and its relatives in the family Polycotylidae are a prime example of this. They look at a glance like small pliosaurs, short neck, large head, 4 big flippers, but when researchers began examining their skeletal anatomy in detail and building phylogenetic trees from those characters, polycotylids consistently came out as something different. Not true pliosaurs in the traditional sense, but a separate group that had independently evolved a compact short-necked body plan. Francis Robin O'Keefe published an important analysis of polycotylid relationships in 2001 that helped clarify this. His work examined the skeletal characters of polycotylids in detail and placed them within a broader plesiosaur phylogeny, and the results were instructive. Polycotylidae, his analysis suggested, was not simply a subset of the large-headed plesiosaur lineage. It was a distinct clade with its own evolutionary history, one that had branched off from earlier plesiosaur stock and developed its compact body plan somewhat independently of the large pliosaurs. This was a meaningful result because it meant that the short-necked body plan had evolved more than once within Plesiosauria, which is a phenomenon called convergent evolution, and it is more common in the history of life than most people initially expect. Later work by Hilary Ketchum and Roger Benson in 2010 revisited plesiosaur phylogeny at a larger scale, incorporating more taxa and more skeletal characters into their analysis. Their results broadly supported the separation of polycotylids from the traditional pliosaur group, while also revealing some of the finer structure within Polycotylidae itself. Where exactly polycotylids branched from the main plesiosaur lineage, and how closely they were related to various other groups, remained a matter of ongoing refinement. But the core finding was consistent. Dolichorhynchops and its relatives occupied a distinct position in the plesiosaur family tree, one that did not map neatly onto the old plesiosaur versus plesiosaur framework. This matters for how we think about the animal. If Dolichorhynchops had been a true pliosaur, closely related to Liopleurodon or Kronosaurus, its evolutionary history would have been one story. It would have inherited its body plan from a lineage of large, powerful apex predators, and perhaps secondarily reduced in size while retaining the general architecture. But if it was a polycotylid that arrived at the short-necked form through a different route, the story of how it became what it was is different. The body plan was not inherited from giants. It was built over evolutionary time by selection pressures, acting on a lineage that was doing something specific in a specific environment. There is also the question of where polycotylids came from in the first place. The family appears in the fossil record during the early Cretaceous, and their origins likely trace back to Jurassic plesiosaur stock. Some researchers have proposed connections to the Romaleosaurids, an early group of plesiosaurs that included both long-necked and relatively short-necked forms. Others have suggested affinities with different early lineages. The honest answer is that the deep origins of Polycotylidae are still not fully resolved, partly because the early Cretaceous plesiosaur record has gaps, and partly because convergent evolution makes it genuinely difficult to distinguish shared ancestry from shared body plan when the characters overlap. What is clearer is the diversity within Polycotylidae once the family is established. Dolichorhynchops is not the only member, and the differences between polycotylid genera are informative. The two recognised species of Dolichorhynchops, Osborni and Herschelensis, are themselves not identical. Dolichorhynchops osborni, the type species described by Williston in 1902, is the better known of the two and comes primarily from the Niobrara chalk of Kansas. Dolichorhynchops herschelensis was described from material found in Saskatchewan, Canada, and shows some differences in skull proportions and tooth morphology. Whether these differences reflect genuine species-level distinctions or simply individual variation and geographic variation within a single species has been a recurring question. There is also a broader issue with specimen assignment that has affected the understanding of Dolichorhynchops over the years. Some specimens originally referred to D. osborni have been re-examined and either reassigned to other taxa or placed in a state of uncertain classification. This is not unusual in paleontology. When a genus is described from incomplete material and subsequent specimens are assigned to it on the basis of apparent similarity, there is always a risk that some of those assignments will turn out to be incorrect as more material accumulates and more rigorous analyses are applied. For Dolichorhynchops, the accumulation of specimens from the Niobrara and from Canadian formations has both clarified and complicated the picture, adding detail while also raising new questions about how much variation was present within the genus. One useful point of comparison is Trinocromerum, another polycotylid from the Niobrara chalk that lived in the same environment at roughly the same time. Trinocromerum bonneri was described by Williston as well, and for a period some specimens were shuffled between Trinocromerum and Dolichorhynchops, as researchers tried to sort out which skeletal characters reliably distinguished the two genera. The current consensus treats them as separate genera, with Trinocromerum being somewhat more robustly built and showing slightly different skull proportions. But their coexistence in the same formation raises interesting ecological questions that we will come back to shortly. The broader polycotylid family tree also includes animals from outside North America, which is important for understanding the evolutionary history of the group. Polycotylids were not confined to the western interior seaway. Their remains have been found in Europe, South America, and elsewhere, suggesting that the group had a wide geographic distribution during the Cretaceous, and that the North American forms represent one regional radiation within a larger global family. This geographic spread implies that polycotylids were capable of crossing open ocean, which is itself an interesting behavioural and physiological inference. An animal that can only function in a specific inland sea cannot colonise multiple continents. The presence of polycotylids on multiple land masses suggests they were capable of open water travel, which in turn supports the idea that they were robust, capable swimmers rather than animals tightly restricted to shallow or sheltered habitats. The cladistic picture that emerges from all of this work is one of a family that evolved relatively early in plesiosaur history, diversified into multiple lineages across different ocean basins, and converged on a compact, fast-moving body plan that was effective for pursuit predation in productive marine environments. Within that family, Dolichorhynchops represents one of the better documented North American forms, but it should be understood as part of a larger evolutionary radiation rather than as an isolated curiosity. There is something philosophically interesting about the classification debates surrounding this animal, and it is worth pausing on briefly. When Williston described Dolichorhynchops in 1902, the goal was straightforward. Name the animal, describe its bones, place it in relation to other known animals. The tools available were primarily morphological. You looked at the shape of the bones, compared them to other specimens, and made a judgment about relationships. That process produced a classification that seemed reasonable given what was known at the time. Over the following century, the tools changed. Cladistics brought a more rigorous, character-based approach to phylogenetic analysis. Computerized methods allowed researchers to process more characters and more taxa simultaneously, producing quantitative assessments of relationship rather than qualitative judgments. The result was not a wholesale rejection of early classifications, but a refinement and in some cases a revision. Animals that had been grouped together because they looked similar were separated when their detailed anatomy revealed different evolutionary histories. Animals that had seemed isolated were connected to relatives in unexpected places. For Dolichorhynchops, this process has produced a clearer picture of what the animal actually was in evolutionary terms. Not a miniature pliosaur, not simply a short-necked plesiosaur, but a polycotylid with a specific evolutionary history, connected to a global family of similar animals, occupying a distinct position in the plesiosaur family tree that reflects both its ancestry and the particular selective pressures of the western interior seaway. That is a more precise and more interesting picture than the one available to Williston in 1902, and it has practical consequences for how the animal is reconstructed and understood. It also has consequences for the questions we ask about its biology. If polycotylids evolved their compact body plan independently of the large pliosaurs, then the functional similarities between the two groups are the product of convergent evolution acting on similar ecological pressures. Both groups were pursuing fast-moving prey in open water. Both groups benefited from a streamlined body and powerful flippers. Both groups developed large skulls with strong jaws and conical teeth. The fact that two separate lineages arrived at similar solutions to similar problems tells us something about the constraints that marine pursuit predation places on body design. There are only so many ways to be an effective fast-moving predator in open water, and the plesiosaur body plan, in its short-necked configuration, represents one of those solutions, arrived at more than once. This kind of convergence is not unique to plesiosaurs. Dolphins, ichthyosaurs and tuna have all converged on streamlined, fast-moving body plans for similar reasons. The ocean rewards efficiency in locomotion, and animals that can move quickly through water with minimal energy expenditure have an advantage over those that cannot. What is interesting about the polycotylid case is that the convergence happened within a single order, between groups that were related but not directly ancestral to one another. It is a smaller scale version of the same phenomenon, playing out within the plesiosaur family tree rather than across the entire history of marine vertebrates. Understanding this evolutionary context does not change the bones of Dolichorhynchops or the deposits of the Niobrara chalk, but it changes how we read those bones. Every character in the skeleton becomes not just a description of what the animal looked like, but a data point in a longer story about how that body plan came to exist, what lineage produced it, what pressures shaped it, and what it tells us about the evolutionary possibilities available to marine reptiles in the Cretaceous. Classification, in this sense, is not just an administrative exercise. It is a way of connecting an individual animal to the broader sweep of evolutionary history, of placing it in a context that makes its existence more legible. And that context, as it turns out, has a direct bearing on how scientists have reconstructed this animal over the decades, both visually and functionally. The picture of Dolichorhynchops that exists today is the product not just of the fossil specimens themselves, but of the evolving understanding of where the animal sits in plesiosaur evolution, what its closest relatives looked like, how its body plan functioned, and what the physical environment of the western interior seaway demanded of its inhabitants. Each revision to the classification has brought with it a set of revised inferences about biology, behaviour and appearance. And the history of those revisions is itself a story worth following, because it shows how scientific understanding of an extinct animal is not a single discovery but an ongoing process of refinement, correction and accumulation. That is where the next part of this story leads. So what does Dolichorhynchops actually look like in the mind's eye of someone trying to picture it honestly? That question turns out to be more complicated than it first appears, and the answer has changed considerably over the past century. The history of how scientists and artists have reconstructed this animal is not just a footnote to the main story. It is a story in itself, one that reflects how paleontology as a discipline has matured, how tools have improved, and how even well-preserved fossil material can be misread when the interpretive framework surrounding it is incomplete. The earliest reconstructions of plesiosaurs, produced in the 19th and early 20th centuries, shared a set of assumptions that now seem almost quaint, though they were perfectly reasonable given what was known at the time. The most persistent of these was the idea that plesiosaurs held their necks above the water surface in the manner of a swan, or perhaps a sea serpent, with the head raised high and the body floating below. This image appeared in popular illustrations, museum displays, and scientific reconstructions alike. It was intuitive. Long necks seemed designed to reach upward, or at least to extend outward in dramatic fashion. The famous 1830 reconstruction by Henri de la Beche, showing Plesiosaurus with its neck arching above the waves while Ichthyosaurus lunged from below, set a visual template that proved remarkably durable. For Dolichorhynchops specifically, the swan neck problem was less severe than for its long-necked relatives simply because the neck was short. But the broader suite of assumptions carried over. Early 20th century depictions of short-necked plesiosaurs and polycotylids often showed them riding high in the water with their bodies partially exposed at the surface, their flippers angled awkwardly, and their overall posture suggesting something closer to a seal, hauling itself onto a rock than a streamlined pursuit predator in open water. The animals looked heavy, sluggish, and somewhat confused about whether they belonged on land or in the sea. Part of this was a failure of comparative biology. Researchers in that era had fewer modern analogues to draw on, and the analogues they did use were not always well chosen. Seals and sea lions, which can move on land and in water, were sometimes used as reference points. Crocodilians, which float at the surface with bodies partially exposed, provided another visual template. Neither was particularly appropriate for a fully pelagic animal like Dolichorhynchops, which almost certainly spent its entire life in open water and had no functional reason to haul out onto land. Its flipper structure was not built for terrestrial locomotion. The bones of the limb girdles do not show the kind of robust attachment points you would expect in an animal that regularly supported its own weight on solid ground. It was, in every structural sense, committed to the water. The shift away from these early depictions began gradually through the mid-20th century and accelerated sharply from the 1980s onward, as biomechanical analysis became a more central part of paleontological work. Researchers began applying principles from fluid dynamics and comparative anatomy to plesiosaur locomotion in a more rigorous way. The question was no longer just what did the bones look like, but how did they actually function, and what constraints did the physics of moving through water place on the animal's posture and behaviour. One of the key insights that emerged from this work concerned flipper orientation. Earlier reconstructions had often depicted plesiosaur flippers moving in a rowing motion, similar to the way oars move through water, pulling back horizontally and then recovering forward. This seemed logical at first glance, but biomechanical modelling suggested a different picture. The structure of the shoulder and hip girdles, combined with the shape of the flippers themselves, pointed toward a motion more like the wing stroke of a penguin or sea turtle. The flippers moved in a figure-8 or figure-of-8-like arc, generating lift and thrust simultaneously, in a manner analogous to an underwater wing rather than a paddle. This is what researchers began calling the underwater flight model, and it had significant implications for how the animal was reconstructed visually. Under the underwater flight model, the body position changes substantially. The animal sits lower and more level in the water, with the flippers angled downward and forward on the power stroke and recovering upward and back. The torso is more horizontal, more streamlined, less of the body breaks the surface, and the overall impression is of an animal that is genuinely hydrodynamic rather than awkwardly buoyant. For Dolichorhynchops, with its compact neck and relatively large flipper surface area, this model produces a reconstruction that looks considerably more athletic than the older depictions. The animal begins to resemble something between a large sea turtle and a very stocky penguin, moving through the water column with controlled, powerful strokes rather than splashing along at the surface, the work of S. Chatterjee and R.J. Templin in 2004 contributed to formalising some of these ideas, applying hydrodynamic modelling to plesiosaur locomotion and producing quantitative estimates of swimming performance. Their analysis suggested that the four-flipper system, when operating in a coordinated fashion, could generate efficient thrust across a range of speeds, with the front and rear flippers potentially working in a phased sequence to reduce turbulence and improve overall efficiency. The short-necked polycotylid body plan, in their model, was particularly well suited to higher speed swimming, because the reduced mass and drag of the compact neck meant that more of the animal's energy could go into forward motion rather than fighting its own hydrodynamics. These modelling studies are not without their limitations, and researchers are generally careful to note them. Fossil bones tell us about skeletal geometry, but they do not directly preserve the soft tissues that would have controlled flipper motion. The precise attachment points of muscles, the flexibility of the flipper joints, the degree of coordination between front and rear pairs, all of these must be inferred from comparative anatomy and biomechanical principles rather than observed directly. Different research teams have produced somewhat different estimates of swimming speed and efficiency depending on the assumptions built into their models. The numbers should be treated as informed approximations rather than precise measurements. But even accounting for these uncertainties, the broad picture that emerges from modern biomechanical work is consistent. Dolichorhynchops was built for speed and sustained pursuit, and its reconstruction should reflect that. CT scanning and three-dimensional digital modelling have added another layer to this process in more recent years. Rather than relying solely on the external surface of bones as revealed by preparation, researchers can now scan specimens and examine their internal structure in detail without cutting into the original fossil. This has opened up questions about bone density and microstructure that were previously inaccessible. In marine reptiles generally, bone density is relevant to buoyancy control. Animals that spend time at the surface tend to have different bone density profiles than those that dive to depth. Pachyostosis, the thickening and densification of bone, is associated with animals that need ballast to maintain neutral buoyancy at depth, while animals that are more surface-oriented often show lighter, more cancellous bone structure. Examining these internal features in polycotylid specimens can potentially tell us something about where in the water column Dolichorhynchops typically operated, though the analysis is complex and the conclusions remain somewhat tentative. Three-dimensional digital models have also allowed researchers to test reconstructions in virtual environments. By building a digital skeleton and adding estimated soft tissue volumes, it is possible to calculate approximate center of mass, buoyancy, and hydrodynamic drag for different body configurations. These models can then be tested against each other to see which configurations are most physically plausible. This kind of virtual testing is not a replacement for direct fossil evidence, but it provides a useful check on reconstructions that might otherwise be based primarily on intuition or artistic convention. If a proposed body shape produces a center of mass that would make the animal wildly unstable in water, that is useful information, even if it does not tell you exactly what the correct shape was. Then there is the question of skin. This is where the honest answer is simply that we do not know, at least not directly. No skin impressions have been found for Dolichorhynchops itself. The Niobrara chalk, for all its remarkable preservation of bones, has not yet yielded soft tissue details for this particular animal. So reconstructions of skin texture and colour are necessarily speculative, though they are not entirely without guidance. The most useful comparative material comes from ichthyosaurs, which are not closely related to plesiosaurs, but occupied similar ecological roles in Mesozoic seas. Several ichthyosaur specimens, particularly from the Holzmaden deposits of Germany, and more recently from Jurassic sites in England, have preserved exceptional soft tissue outlines and even traces of skin texture. These show a smooth, streamlined body surface without obvious scales, more similar to the skin of a modern dolphin or tuna than to the scaly skin of a lizard or crocodile. The skin appears to have been relatively tight over the body, with no loose folds or prominent surface features that would increase drag. Whether plesiosaurs had similar skin is not certain. They were not ichthyosaurs. They evolved their aquatic lifestyle independently, and the details of their integument may have differed. But the physical logic is similar. An animal that moves fast through water benefits from a smooth, low-drag surface, and the evolutionary pressures acting on a pursuit predator in the open ocean would tend to favour smooth skin over rough or heavily textured skin. Most modern reconstructions of Dolichorhynchops therefore depict it with smooth, relatively featureless skin, similar to a large marine mammal, though with the caveat that this is an inference rather than a documented fact. Colour is even more uncertain. No pigmentation evidence has been preserved for any plesiosaur. The colours used in reconstructions are entirely conjectural. That said, there is a principle from modern marine animals that is commonly applied. Countershading, the pattern in which an animal is darker on its dorsal surface and lighter on its ventral surface, is extremely widespread among open water predators. Dolphins, sharks, tuna, penguins, and many other animals show this pattern, and the functional explanation is straightforward. When viewed from above, a dark dorsal surface blends with the deep water below. When viewed from below, a light ventral surface blends with the bright surface above. Countershading reduces visibility from both directions, which is useful both for hunting and for avoiding being hunted. Given that Dolichorhynchops was both a predator and potential prey in the western interior seaway, countershading would have been functionally advantageous, and most serious reconstructions apply some version of it, typically a dark grey or blue-grey on the back, and a lighter grey or off-white on the belly. But this is applied reasoning, not evidence. The actual colours could have been quite different. There is something worth sitting with in all of this. The reconstruction of an extinct animal is never a single act. It is an accumulation of decisions, each one made at the intersection of what the fossils show, what physics and biology constrain, and what analogy from living animals suggests. Some of those decisions are well supported. The basic body shape of Dolichorhynchops is established by multiple well-preserved specimens. The locomotion model is grounded in biomechanical analysis. The diet inference comes from tooth morphology, and stomach content evidence from related animals. Other decisions are much softer. The skin texture is a plausible guess. The colour is an educated analogy. The precise coordination of flipper strokes during a high-speed chase is a model, not an observation. What has changed most dramatically over the past century is not the quality of the fossils themselves, though new specimens have certainly added detail. What has changed is the interpretive toolkit brought to bear on those fossils. Early reconstructions were produced by researchers who were skilled at describing bones but had limited access to the biomechanical and comparative biological frameworks that modern paleontologists use routinely. The result was not bad science for its time, but it was incomplete science, and the incompleteness showed up most visibly in the reconstructions that accompanied it. The progression from the swan-necked surface-floating plesiosaur of early museum dioramas to the streamlined, actively swimming polycotylid of modern scientific illustration is a record of that interpretive evolution. Each revision has been driven not by the discovery of new bones alone, but by the development of new questions and new methods for answering them. The bones of Dolichorhynchops that Williston described in 1902 are not fundamentally different from the bones that researchers examine today. But the questions asked of those bones and the tools available to answer them have changed enormously. And the reconstruction that results from that changed inquiry looks, moves, and behaves quite differently from the animal that appeared in the earliest scientific literature. This ongoing process of revision is not a sign of weakness in paleontology, it is a sign of health. A field that never revises its reconstructions in the face of new evidence and new methods is a field that has stopped asking questions. The fact that our picture of Dolichorhynchops has changed and will likely continue to change as new specimens are found and new analytical methods are developed, is precisely what makes it a living area of scientific inquiry rather than a closed historical record. The animal itself stopped changing 65 million years ago or more. The science surrounding it has not, and as the reconstruction has become more precise, more physically grounded, and more biologically informed, it has also become more useful as a lens for understanding the broader ecosystem in which Dolichorhynchops lived. A more accurate picture of how the animal moved tells us more about how it hunted. A better understanding of its hunting strategy tells us more about what it ate. A clearer sense of what it ate tells us more about its ecological role in the seaway. Each refinement in the reconstruction ripples outward into a richer understanding of the world it inhabited, which brings the story naturally to the question of how Dolichorhynchops related to the other polycotylids sharing the world's oceans at the same time, and what the global distribution of its family reveals about the reach and diversity of this particular branch of plesiosaur evolution. Dolichorhynchops was not alone in its family. That's worth pausing on for a moment, because it is easy to study a single animal in isolation and forget that it existed within a much larger biological context, not just an ecological one, but an evolutionary one. The polycotylids were a genuinely widespread group. They were not confined to the western interior seaway, not limited to North America, and not restricted to any single geological moment within the Late Cretaceous. They were distributed across the world's oceans during a period when those oceans were warm, connected in ways they are not today, and full of life in densities that are difficult to imagine from where we stand now. Within the Niobrara deposits of Kansas and Nebraska, the animal most directly comparable to Dolichorhynchops is Trinachromerum. The two genera overlapped in both time and space, which immediately raises a question that ecologists find interesting and paleontologists find difficult to answer cleanly. When two similar predators occupy the same environment at the same time, what happens? The straightforward answer from modern ecology is that they either compete directly, with one eventually displacing the other, or they partition the available resources in some way that allows both to persist. The fossil record rarely tells us which of these was happening, but the anatomical differences between Trinachromerum and Dolichorhynchops offer some clues worth considering. Trinacromerum bonneri, the species found in the Niobrara, was broadly similar to Dolichorhynchops in its general body plan. Short neck, large flippers, elongated skull, conical teeth. But the proportions were not identical. Trinacromerum tended to have a slightly broader skull relative to its length, and some specimens suggest a marginally more robust body build. These are not dramatic differences. They are the kind of subtle anatomical variation that might not seem important at first glance. But in ecology, small differences in body proportions can translate into meaningful differences in prey preference or hunting depth. A slightly broader skull with a marginally different jaw geometry might favour slightly different prey sizes, or slightly different strike angles, or slightly different water depths where hunting was most efficient. None of this is proven for these two animals specifically, but the principle is well established in modern ecosystems. Closely related predators living in the same waters almost always show some degree of niche separation, even when it is not immediately obvious from a distance. It is also worth noting that the Niobrara deposits, for all their richness, compress a significant span of time into their layers. Animals that appear to co-occur in the same formation may not have been truly contemporaneous at the level of individual decades or centuries. Two species that appear to overlap in a geological sense may have actually peaked at slightly different times within that formation, with one declining as the other became more common. Disentangling this kind of fine-grained temporal pattern from a fossil record is extremely difficult, and for the Niobrara polycotylids, the resolution is not yet precise enough to say definitively whether Dolichorhynchops and Trinacromerum were genuine contemporaries competing in the same waters at the same time, or whether they alternated in dominance across the formation's depositional history. Moving beyond North America, the polycotylid family extends into Europe and South America in ways that reveal something interesting about the connectivity of late Cretaceous oceans. European polycotylids have been described from England and France, from deposits of broadly similar age to the North American material. South American forms have been found in Colombia and Argentina. The presence of closely related animals on multiple continents separated by open ocean raises the question of how they got there and what it tells us about the seaways and current systems of the late Cretaceous world. The short answer is that the late Cretaceous was a period of unusually high sea levels and extensive shallow epicontinental seas. The continents were not arranged as they are today. The Atlantic Ocean was younger and in some places narrower. Tethys, a vast warm ocean that once separated the northern and southern land masses, was still a major feature of the global ocean system. The world's oceans were more interconnected than they are now, and warm shallow seas extended across regions that are today dry land. For a mobile marine predator like a polycotylid, crossing between what would become Europe and North America was not necessarily the same barrier it would be today. There were likely shallow, warm, productive corridors through which animals could disperse, following prey populations and favourable conditions across what are now very different ocean basins. This kind of biogeographic thinking is not unique to plesiosaurs. Many late Cretaceous marine groups show similar patterns of wide distribution. Mosasaurs, for example, were found on virtually every continent by the end of the Cretaceous. Certain shark genera appear on multiple continents in deposits of similar age. The oceans of the late Cretaceous were, in a meaningful sense, a more unified system than the oceans of today, and the animals living in them moved through that system in ways that reflected its connectivity. Polycotylus latipinis deserves particular mention here, partly because it is closely related to Dolichorhynchops, and partly because it is the animal at the centre of one of the most significant plesiosaur discoveries of recent decades. Polycotylus was a North American polycotylid with a somewhat larger, more robust body than Dolichorhynchops. Its skull was proportionally shorter and broader. It was not quite the same kind of sleek pursuit predator that Dolichorhynchops appears to have been, though it was certainly an active swimmer and a capable hunter. The remarkable specimen described by O'Keefe and Chiappe in 2011, the one containing a near-term fetus inside the body cavity, was a polycotylus. And because Polycotylus and Dolichorhynchops were both polycotylids, sharing a common ancestor and a broadly similar biology, the implications of that discovery extend across the family. Leave birth was almost certainly a polycotylid trait, not a Polycotylus-specific one. Edgarosaurus muddy is another polycotylid worth mentioning, found in the Thermopolis Shale of Wyoming and dating to the early Cretaceous, which makes it one of the earlier members of the family. It was smaller than Dolichorhynchops, with somewhat different body proportions, and its presence in early Cretaceous deposits suggests that the polycotylid lineage had already diverged from other plesiosaur groups well before the late Cretaceous, giving the family time to diversify and spread before the Western Interior Seaway reached its maximum extent. Edgarosaurus helps anchor the temporal depth of the polycotylid story, reminding us that Dolichorhynchops was not the beginning of this lineage, but one of its later, highly refined expressions. Within the broader plesiosaur family tree, polycotylids occupy a position that has been the subject of considerable debate. Plesiosauria as a whole is divided into two major groups: the plesiosauromorphs, which include the long-necked forms like Elasmosaurus, and the pleosauromorphs, which include the large-headed, short-necked forms like Kronosaurus and Leopleurodon. For a long time, the short-necked polycotylids were assumed to be most closely related to the pleosauromorphs, since they shared the short neck and large skull. This seemed logical enough on the surface. Short neck in one group, short neck in another group, probably related. But phylogenetic analysis has complicated this picture considerably. Work by researchers including F. Robin O'Keefe in 2001, and later by Hilary Ketchum and Roger Benson in 2010, suggested that polycotylids are not actually plesiosauromorphs at all. Instead, they appear to be more closely related to the plesiosauromorphs, the long-necked forms, which means that the short neck in polycotylids evolved independently from the short neck in true plesiosaurs. This is an example of convergent evolution, where similar body shapes arise in different lineages because similar environmental pressures favour similar solutions. A short neck, large skull, and powerful flippers are a useful combination for a fast pursuit predator in open water, and natural selection arrived at this configuration more than once within Plesiosauria. This finding matters for how we interpret Dolichorhynchops. If polycotylids are genuinely closer to elasmosaurids than to pliosaurs, then the last common ancestor of Dolichorhynchops and Elasmosaurus was probably a moderately long-necked animal, and the compact body plan of Dolichorhynchops represents a secondary shortening and reorganization of the neck, rather than an ancestral condition. This is a meaningful distinction. It tells us that the polycotylid body plan was not simply inherited from an ancient short-necked ancestor, but was actively shaped by selection pressures favouring speed and pursuit capability. The compact body of Dolichorhynchops is not a primitive feature. It is an advanced one. The species-level taxonomy within Dolichorhynchops itself has also seen some revision. The original species, Dolichorhynchops osborni, named by Williston in 1902, remains the most thoroughly documented. A second species, Dolichorhynchops herschelensis, was described from material found in Saskatchewan, Canada, in deposits of slightly different age and paleogeographic context. Some specimens that were originally referred to Dolichorhynchops have subsequently been reassigned to other genera as researchers have examined the material more carefully and applied more rigorous phylogenetic criteria. This kind of taxonomic revision is entirely normal in paleontology. Early workers often group together animals that later analysis separates, and the boundaries between genera and species in the fossil record are frequently less clear than they appear in a textbook list. What the global distribution of polycotylids ultimately suggests is that this was a successful, adaptable family. Not the largest plesiosaurs, not the most anatomically extreme, but well designed for what they did, and capable of spreading across the world's warm Cretaceous oceans in a way that speaks to both their mobility and their ecological flexibility. Different polycotylid species occupied different seas, different depths, different prey communities, and different positions in different food webs. Dolichorhynchops in the Western Interior Seaway was one expression of this family's range. The European forms were another. The South American forms were another still. Each adapted to its own particular ocean, its own particular prey, its own particular set of predators and competitors. There is something quietly impressive about this. Polycotylids were not the apex predators of their world. They did not dominate the late Cretaceous oceans the way Mosasaurs eventually would. They were not the most famous animals in the Niobrara, not the ones that appear most often on museum marquees or documentary thumbnails. That distinction goes to Tylosaurus, to Elasmosaurus, to Pteranodons soaring overhead. But polycotylids persisted, diversified, and spread across the globe during one of the most ecologically competitive periods in the history of marine life. That is not a small achievement. It suggests a level of ecological competence that their relatively modest size and fame might cause us to underestimate. Dolichorhynchops, specifically, represents the polycotylid body plan at something close to its most refined. The combination of speed, maneuverability, precise dentition, and sensory capability that the anatomy suggests was not accidental. It was the product of tens of millions of years of plesiosaur evolution, filtered through the particular selective pressures of the western interior seaway, shaped by the prey available, the predators present, and the physical characteristics of a warm, productive, enclosed inland sea. Every feature of the animal, from the narrow snout to the large forward-positioned eyes, to the compact neck to the powerful flippers, reflects the specific demands of that specific environment, and yet, for all its specialization, for all the elegance of its adaptation to the seaway, that specialization carried a cost. The very precision with which Dolichorhynchops was fitted to its world made it dependent on that world continuing to exist. When the western interior seaway began to change, the ecological foundation on which polycotylids like Dolichorhynchops had built their success began to shift beneath them. The warm, productive, shallow sea that had supported their lineage for millions of years was not a permanent feature of the planet. It was a temporary one, created by specific geological and climatic conditions that were already beginning to change. The story of how that change unfolded, and what it meant for Dolichorhynchops and the entire community of animals that shared its world, is where the narrative turns next. The western interior seaway was not a permanent ocean. It never had been. It was a geological accident, a consequence of a specific combination of conditions that happened to align during the late Cretaceous, and then, over millions of years, slowly stopped aligning. Understanding why it disappeared requires stepping back from the animals that lived in it and looking at the larger forces that created and then dismantled the world they depended on. The seaway existed because the sea level during the Cretaceous was extraordinarily high by modern standards. Global temperatures were warmer, the polar ice caps were minimal, and the thermal expansion of ocean water, combined with the displacement caused by active mid-ocean ridge systems, pushed sea levels perhaps 100 to 200 meters higher than they are today. This was enough to flood the low-lying interior of North America, creating a continuous marine corridor from the Arctic to the Gulf of Mexico. That corridor had existed in various forms since the early Cretaceous, and at its peak it was a fully functioning marine ecosystem, rich, productive, and ecologically complex. But it was always sitting on borrowed time, in a geological sense. The force that ended it was the Laramide orogeny, the mountain-building event that raised the Rocky Mountains. This process began roughly 70 to 75 million years ago, driven by the subduction of the Farallon Plate beneath the western edge of North America. As the plate descended at an unusually shallow angle, it created compressional forces far inland from the subduction zone itself, pushing up the crust in broad, sweeping uplifts that would eventually become the mountain ranges we recognize today. The Rocky Mountains did not rise overnight. They grew slowly, incrementally, over millions of years. But as they rose, they tilted the interior of the continent. Land that had been below sea level began to lift. The shallow basin that held the seaway began to drain from the west. The regression of the seaway was not a single dramatic event. It was a drawn-out process, a gradual retreat of the shoreline, a slow shallowing of the water column, an incremental loss of the marine habitat that had supported so many animals for so long. By around 70 million years ago, the seaway had begun to split into a northern and southern portion. By approximately 68 million years ago, the two portions had largely separated, and by the end of the Cretaceous, around 66 million years ago, the seaway had retreated almost entirely, leaving behind the continental interior that would eventually become the Great Plains. For Dolichorhynchops, this process was catastrophic. Not suddenly and dramatically catastrophic, but catastrophic in the slow, grinding way that ecological collapse tends to work. The seaway was not just the water Dolichorhynchops swam in, it was the entire structure of the world it depended on. The warm, shallow conditions supported the planktonic productivity that fed the fish that Dolichorhynchops pursued. The enclosed basin maintained the particular temperature and salinity gradients that the seaway's food web was built around. The specific geography of the seaway, its depth, its extent, its connectivity to the open ocean, shaped everything from prey distribution to migration patterns to the availability of breeding habitat. When the seaway began to change, all of these things began to change with it. Dolichorhynchops disappears from the fossil record noticeably before the end Cretaceous mass extinction at 66 million years ago. This is an important point. The animal did not survive until the asteroid impact at Chicxulub, and then die in the global catastrophe, along with the non-avian dinosaurs and the Mosasaurs. It was already gone, or nearly gone, before that final extinction event. The polycotylid family as a whole appears to have declined significantly through the late Campanian and into the Maastrichtian, the final stage of the Cretaceous. By the time the mass extinction arrived, polycotylids were already a shadow of what they had been. The fossil record in the Niobrara chalk captures Dolichorhynchops during its peak, during the Campanian stage when the seaway was still broad and productive and the ecosystem it supported was still largely intact. The specimens from Kansas and Nebraska represent animals living in a world that was, in geological terms, not far from its end. But they had no way of knowing that, of course. The seaway was still warm, still full of fish, still dangerous with mosasaurs and sharks. Life in the seaway during the late Campanian was as intense and competitive as it had ever been. The changes that would ultimately drain that world were happening far to the west, in the slow upward creep of rock and sediment that would one day become mountains. What the pattern of polycotylid decline suggests, when you look at it carefully, is something that ecologists recognise as a recurring pattern in extinction events, both ancient and more recent. Animals that are tightly specialised to a specific environment tend to be more vulnerable to environmental change than animals with broader ecological tolerances. Dolichorhynchops was exquisitely fitted to the western interior seaway. Its body plan, its hunting strategy, its prey base, its reproductive biology, all of it was calibrated to the specific conditions of that specific body of water. That specialisation was an enormous advantage as long as the seaway remained stable. It became a liability the moment the seaway began to change. Compare this to the elasmosaurids, the long-necked plesiosaurs that shared the seaway with Dolichorhynchops. Elasmosaurids persisted longer into the Cretaceous, with some genera surviving close to the end Cretaceous boundary. They were also present in other ocean basins beyond the western interior seaway, which meant that the regression of the seaway, while certainly harmful to elasmosaurid populations there, did not eliminate the entire group the way it effectively eliminated the polycotylids. The mosasaurs, which were the dominant marine reptiles of the final stages of the Cretaceous, were similarly broad in their distribution, present in oceans worldwide and capable of tolerating a wider range of conditions. They persisted until the very end, when the asteroid impact and its aftermath finally ended their lineage along with so much else. This pattern of selective survival and selective extinction is not random. It reflects the relationship between specialization and resilience. A highly specialized animal in a stable environment is an efficient machine. It does exactly what it needs to do. Nothing wasted, nothing superfluous. But efficiency built around stability is fragile in the face of change. The very features that make Dolichorhynchops so interesting to study, its precisely adapted teeth, its streamlined body, its apparent dependence on the particular prey community of the seaway, are also the features that made it vulnerable when the environment that shaped those adaptations began to dissolve. There is something worth sitting with in that observation. It is not a comfortable one exactly, but it is honest. The seaway was not destroyed by any single catastrophic event, not by a volcanic eruption, not by a sudden climate shift, not by anything that happened quickly enough to be called a disaster in the human sense of the word. It was dismantled by geology, by the slow, patient rise of mountains, by the gradual tilting of a continent, by processes that operated on timescales so vast that no individual animal, no population, no generation could have perceived them as change at all. From the perspective of any given Dolichorhynchops, the world was simply the world. The water was there, the fish were there, the sun filtered down through the same warm shallows it always had. The Mosasaurs were still dangerous. The days continued, and yet the world was ending, in the only way worlds tend to end, slowly, and then all at once. As the seaway shallowed and fragmented, the ecological community it supported began to unravel. Prey populations shifted. The warm, productive conditions that had supported enormous densities of fish and cephalopods became patchier, less reliable, less consistent. The physical habitat that polycotylids needed for reproduction, for birth, for the early development of their young, became less available. The population of Dolichorhynchops, which had never been enormous by the standards of smaller, faster reproducing animals, began to thin. Fewer individuals survived to reproductive age. Fewer young were born. The genetic diversity that allows a population to adapt to changing conditions narrowed. The decline, once it reached a certain point, would have become self-reinforcing. It is worth noting that we cannot trace this decline in detail from the fossil record. The Niobrara chalk captures a window of time, not a continuous film. The specimens we have represent moments of preservation, animals that happen to die in conditions favourable to fossilization, whose bones happen to survive long enough to be found. The gaps between specimens are enormous. We can say that Dolichorhynchops appears in the Campanian and does not appear in the Maastrichtian, but the fossil record cannot tell us exactly when the last individual died, or where, or under what circumstances. The disappearance is real, but the details of it are lost. What we can say is that by the time the Maastrichtian began, roughly 72 million years ago, polycotylids as a group were in serious decline. The western interior seaway was already contracting. The rich Niobrara ecosystem that had produced such an extraordinary diversity of marine life was fragmenting. The ecological relationships that had sustained animals like Dolichorhynchops for millions of years were breaking down. The seaway was becoming a series of disconnected basins, each smaller and shallower than the whole had been, each less capable of supporting the complex food web that the whole had maintained. And then, 66 million years ago, the asteroid arrived. The Chicxulub impactor struck the shallow seas of what is now the Yucatan Peninsula, releasing energy equivalent to billions of nuclear weapons, triggering wildfires across much of the planet, sending enormous quantities of debris into the upper atmosphere, blocking sunlight, collapsing photosynthesis, and unravelling food webs from the bottom up. The mass extinction that followed was among the most severe in the history of complex life on Earth. Roughly 3/4 of all species went extinct. The non-avian dinosaurs disappeared. The pterosaurs disappeared. The mosasaurs, which had survived everything the Cretaceous had thrown at them up to that point, disappeared. The ammonites, which had been present in Earth's oceans for hundreds of millions of years, disappeared. For Dolichorhynchops, this final catastrophe was almost beside the point. The animal was almost certainly already gone, or reduced to such small and isolated remnant populations that the mass extinction simply erased whatever remained. The seaway it had lived in was already a fraction of its former self. The ecosystem it had depended on was already gone. The KPG extinction was the final punctuation on a sentence that the Laramide orogeny had already been writing for millions of years. There is a certain melancholy in this, if you let yourself feel it. Not just for Dolichorhynchops specifically, but for the entire world of the western interior seaway. The Mosasaurs, the Elasmosaurids, the sharks, the enormous fish, the ammonites, the diving birds, the whole extraordinary community of life that had filled that warm inland sea for tens of millions of years, all of it gone. Not just the animals, but the sea itself. The water drained away, the sediments accumulated, the land rose, and what had been an ocean floor became a prairie. The chalk and limestone that had formed on the seaway's bottom became exposed at the surface of Kansas and Nebraska and South Dakota, preserving within them the bones of everything that had once lived above. In a sense, the Niobrara chalk is the seaway's memorial. It is what the seaway left behind when it retreated. Layer after layer of fine sediment, each one representing years or decades of slow accumulation, each one containing within it the fragments of the world that existed above. The bones of Dolichorhynchops embedded in that chalk are not just fossils. They are the physical residue of a living animal in a living ecosystem, preserved by the same geological processes that eventually destroyed the world it inhabited. There is something almost symmetrical about that. The conditions that allowed the seaway to exist also created the conditions for its remarkable preservation. The fine-grained sediments that accumulated in the quiet, shallow waters were ideal for entombing bones before scavengers or decay could fully dismantle them. The very productivity of the ecosystem, the enormous quantities of organic material raining down onto the seafloor, contributed to the anoxic conditions in the sediment that slowed decomposition and allowed mineralization to occur. The seaway preserved its own history even as it was disappearing. What remains of Dolichorhynchops now is bones in museums, measurements in papers, reconstructions in textbooks, and a name that most people have never heard. But those bones carry an extraordinary amount of information. They tell us about an animal that was genuinely fast, genuinely capable, genuinely well adapted to one of the most competitive marine ecosystems the Cretaceous world produced. They tell us about a reproductive strategy that links plesiosaurs to modern live-bearing marine mammals in ways that feel surprisingly intimate. They tell us about a predator that was itself prey, that bore injuries and healed from them, that occupied a precise position in a food web of remarkable complexity. And they tell us something about the nature of ecological success. Dolichorhynchops was, by any reasonable measure, a successful animal. It persisted for millions of years in a demanding environment. It diversified into multiple species. It spread across a significant portion of the North American interior sea. It refined its body plan to a degree of efficiency that still impresses researchers studying it more than a century after the first specimens were described. It was not a failed experiment. It was not a marginal creature clinging to the edges of its ecosystem. It was a central participant in one of the most productive marine environments of the Mesozoic era. That it is gone now is not evidence of failure. It is evidence of change. The world it was built for ceased to exist, and no amount of evolutionary refinement could have prepared it for that. This is the quiet lesson that Dolichorhynchops offers, not a dramatic one, not a cautionary tale in the simple sense, but something more honest and more patient. Specialization is not a mistake, it is a strategy, and like all strategies, it works until the conditions that made it work no longer apply. The bones in the Niobrara chalk are what remain, and what they point toward, beyond the extinction and the vanished sea and the animal itself, is something that the last section of this story is perhaps better suited to hold. There is a particular kind of satisfaction that comes from studying an animal that the fossil record has treated generously. Not all prehistoric creatures are so lucky. Many are known from a single tooth, a partial jawbone, a fragment of vertebra pulled from a riverbank and interpreted with enormous effort and considerable uncertainty. The picture they leave behind is blurry, approximate, a rough sketch where you'd like a portrait. Dolichorhynchops is different. Multiple specimens, multiple species, a pregnant relative preserved in extraordinary detail, bones with healed injuries that speak to individual lives, individual encounters, individual moments of survival. A body plan well enough preserved that researchers have been able to run hydrodynamic models, estimate swimming speeds, reconstruct muscle attachments, and argue productively about flipper posture. For a creature that lived roughly 85 million years ago in a sea that no longer exists, that is a remarkable amount of information to have, and yet most people have never heard the name. Ask someone to name a prehistoric marine reptile and they will say Mosasaurus, or perhaps Plesiosaurus, or if they have been paying close attention to recent natural history programming, maybe Elasmosaurus with its improbable neck. Dolichorhynchops does not appear in most lists. It does not have a memorable silhouette in the popular imagination. It has not been featured in many films or television programs. It sits in the literature, carefully described, well understood within its field, and almost entirely invisible to the wider world. There is something mildly ironic about that. One of the best documented predators of the Cretaceous seas, and it remains for most people simply unknown. But perhaps that is part of what makes it worth sitting with for a while. The animals that become famous tend to be the largest, the most dramatic, the most visually extreme, the ones that fit easily into a poster or a toy line. Dolichorhynchops was not the largest thing in its sea, it was not the apex predator, it was not the longest or the most heavily armoured or the most visually arresting. It was something more interesting than any of those things. It was precise, it was refined. It was a solution to a specific problem, built by millions of years of selection pressure in a specific environment, and it worked. It worked well enough that it persisted across a significant stretch of geological time, diversified, spread, and left behind enough of itself that we can still reconstruct its life with genuine confidence more than 80 million years after it died. There is a researcher named Samuel Wendell Williston who described the first Dolichorhynchops specimens in 1902, working from material pulled out of the Niobrara chalk of Kansas. Williston spent a significant portion of his career working through the fossils of the Western Interior Seaway, and he understood better than most people of his era just how extraordinary that chalk formation was. The Niobrara is not just a fossil site, it is a window. A wide, detailed, generously preserved window into a world that would otherwise be almost entirely invisible to us. Williston and the researchers who came after him, through the 20th century and into the 21st, have spent careers peering through that window, and what they have seen is an ecosystem of staggering complexity and richness. Dolichorhynchops is one of the clearest figures visible through that glass. The Niobrara chalk itself deserves a moment of quiet appreciation. It stretches across parts of Kansas, Nebraska, and South Dakota, and in places it is exposed at the surface in outcrops that have been eroding slowly for centuries, releasing their contents into the hands of anyone patient enough to look. The chalk was deposited over millions of years on the floor of the Western Interior Seaway, grain by grain, organism by organism, the accumulated remains of countless tiny creatures raining down through the water column and settling into the sediment. What looks like featureless white rock is, on examination, a record of extraordinary biological productivity. And embedded within it, at intervals, are the larger things. The mosasaurs and plesiosaurs and fish and birds that lived in the water above and sank to the bottom when they died, or were carried there by currents, or came to rest in the quiet deep and were slowly buried and slowly mineralized and slowly transformed into the fossils that Williston and his colleagues and their successors have spent more than a century carefully extracting. Every bone that comes out of the Niobrara is a small act of recovery, something that was alive, that moved through water, that hunted and was hunted, that breathed and reproduced and died, preserved long enough for us to find it and ask questions of it. The fact that we can do this at all still seems, on reflection, slightly improbable. That the conditions were right, that the sediment was fine enough, that the chemistry was favourable, that the bone survived millions of years of geological change, that the formation was exposed at the surface in a place where people eventually thought to look, that those people had the training and the curiosity to recognize what they were seeing. All of it had to align, and it did, repeatedly. The Niobrara has been yielding specimens for well over a century, and it has not exhausted itself yet. The western interior seaway that those specimens came from is, in its own way, one of the most fascinating geographical facts of North American history. Not human history, geological history. For tens of millions of years, the continent was divided. There was no continuous landmass from the Gulf of Mexico to the Arctic. There was water, warm and shallow, and enormously productive, stretching across the middle of what is now the Great Plains. The Rocky Mountains had not yet fully risen. The land was lower, the sea was higher, and the interior of the continent was submerged beneath a body of water that would have dwarfed any modern inland sea. The Caspian Sea, the largest lake on Earth today, is roughly 370,000 square kilometers. The western interior seaway, at its maximum extent, covered something on the order of 1.5 million square kilometers. It was not a lake. It was an ocean passage, connected to the Arctic and the Gulf, flushed by currents, stratified by depth and temperature, home to an ecosystem that had no modern equivalent. That sea is gone now, completely gone. The water drained away, the sediments compacted, the land rose, and the prairie replaced the seabed. The animals that lived in it are gone too. Not just reduced or relocated, but genuinely extinct. Every lineage, every species, every ecological role they played. The Mosasaurs are gone. The polycotylids are gone. The elasmosaurids are gone. The enormous fish like Zephactinus are gone. The ammonites that drifted through the water column for hundreds of millions of years are gone. The diving birds, the sharks that scavenged the dead, the cephalopods that Dolichorhynchops pursued in the dim middle water, all of them gone. The entire community, the entire interlocking web of relationships and dependencies and evolutionary histories, erased. And yet, here we are, talking about it, reconstructing it. Not perfectly, not completely, not without uncertainty, but with genuine substance. We know what the seaway looked like. We know its approximate dimensions and depth and temperature. We know which animals lived in it, and roughly what they ate and how they moved and how they reproduced. We know how the ecosystem was structured, who ate whom, which animals were abundant and which were rare, how the food web was organised from the microscopic plankton at the base to the large mosasaurs at the top. We know this because the Niobrara chalk preserved it, and because generations of researchers have had the patience and the skill to read what the chalk recorded. Dolichorhynchops sits near the centre of that reconstruction, not because it was the most dominant animal in the seaway, but because it is one of the most completely understood. Its anatomy is well documented, its ecology can be reasonably inferred, its reproductive strategy, by extension from its close relative Polycotylus, is now understood to have involved live birth, which connects it to the broader biology of large marine vertebrates in ways that feel genuinely illuminating. Its position in the food web is clear enough that it anchors our understanding of the mid-level predator community of the seaway. When researchers model how the seaway ecosystem functioned, Dolichorhynchops is one of the data points solid enough to build around. There is something quietly moving about that if you think about it from a certain angle. This animal lived and died in a sea that no longer exists. It left its bones in sediment that accumulated over millions of years on a seafloor that is now exposed prairie. Those bones were found by researchers working in the late 19th and early 20th centuries, described and catalogued and argued over, and they have been studied ever since, with increasingly sophisticated tools and increasingly refined questions. And through all of that, the animal has gradually come back into focus. Not back to life, but back to understanding. We know what it looked like. We know roughly how it moved. We know what it ate and how it caught its food. We know how it was born and how it grew and what killed it and what ate it when it was dead. We know the world it lived in with enough detail that we can place it within that world and watch it, in imagination, moving through the warm green water of the Cretaceous interior sea. That is what paleontology does at its best. It does not simply catalogue the dead, it reconstructs the living. It takes fragments of bone and stone and turns them slowly and carefully into something that was once alive and present and real. And the better the fossil record, the better the reconstruction, and the more completely a vanished world can be recovered. The Niobrara chalk is one of the places on Earth where that recovery is most complete, and Dolichorhynchops is one of the animals through which that world can be most clearly seen. If you've been listening tonight from somewhere quiet, from a room settling into darkness, or a bed where the day is finally loosening its hold, perhaps you've had a moment to sit with the image of that sea, the warm surface water catching light, the slow movement of ammonites through the middle depths, the sudden acceleration of something compact and fast, 4 flippers driving through the water in long, powerful strokes, a narrow snout angled toward a school of silver fish scattering in all directions. The seaway going about its business, indifferent to the fact that it would one day be gone, indifferent to the fact that millions of years later someone would find its bones and its chalk and its fossils and try to understand what it had been. There is a question worth sitting with as you settle toward a sleep tonight, and it is not a frightening one. It is more of a gentle puzzle. How many worlds like this one have existed and vanished without leaving enough behind to be reconstructed? The Western Interior Seaway was lucky, in geological terms. Its sediments were fine-grained and preserving. Its location was later exposed at the surface where people could find it. Its animals were large enough to leave substantial bones. Other seas, other ecosystems, other communities of extraordinary animals may have come and gone without leaving anything we could ever read. The history of life on Earth that we can reconstruct is, in all likelihood, a small fraction of the history that actually occurred. The Niobrara is one of the windows we have. Dolichorhynchops is one of the faces visible through it. And perhaps that is the gentlest reason to care about an animal most people have never heard of. Not because it was the largest or the most powerful or the most dramatic, but because it is there, in the record, clearly enough to see. Because the people who found it and described it and studied it over more than a century did careful, patient work that has given us something real to hold on to. Because the world it lived in was genuinely extraordinary, and Dolichorhynchops is one of our clearest guides to what that world was like. Because understanding it well means understanding the seaway well, and understanding the seaway means understanding something true about the deep history of the continent beneath your feet, wherever you are listening from tonight. The Niobrara chalk will continue to give up its fossils slowly. Erosion does not stop. Researchers will continue to find new specimens, ask new questions, apply new methods. The picture of Dolichorhynchops and its world will continue to sharpen, detail by detail, paper by paper, specimen by specimen. That is how this kind of knowledge works. Not in sudden revelations, but in the slow accumulation of careful observation. The same way the chalk itself formed, one grain at a time, over millions of years, until it held within it everything we needed to know. So wherever you are tonight, whatever the hour, whatever the temperature outside your window, I hope this journey through a vanished sea has been a comfortable one. I hope the image of that warm Cretaceous water and the compact, fast, carefully built animal moving through it has settled into your thoughts in a way that feels worth keeping. Dolichorhynchops will not be in the headlines. It will not appear on a billboard or a lunchbox. But it was real, and it was remarkable, and thanks to the chalk and the researchers and the long patient work of paleontology, it is knowable. That seems like enough. That seems, honestly, like quite a lot. Thank you for spending this time here. If tonight's story gave you something to think about, or simply gave you a quiet place to rest while the world outside did its thing, it would mean a great deal if you left a like or a comment, or subscribe to Life Beyond Scene so the next story finds its way to you. I read the comments when I can, and I'm always genuinely curious where people are listening from, what drew them to a particular topic, what they found surprising or beautiful or strange. This is a small and unhurried corner of the world, and I am glad you found it. Sleep well tonight. The sea is gone, but the bones remain, and the story, for now, is told.